Okay, thank you very much. So this was my joint work with Stefan Račan from the Czech Academy of Sciences, and let's get right into it. So what I will be talking about is temporal logics for model checking. Model checking is a decision problem whether a system is a model of some temporal logic property. And we have a lot of temporal logics. Commonly used are, for example, the linear time logic, LTL, the computation tree logic, CTL, and the strongest usually considered temporal logic is the propositional Mie calculus. Now, unfortunately, the classic model checking scales quite poorly unless some techniques such as abstraction refinement are used. And counterexample guided abstraction refinement has taken the world by a storm. It is a huge success, but unfortunately it can only verify path universal properties. And that means it cannot actually verify all of the logics, all of the logics that are involved. Okay. So CTL star, Mie calculus, there are some properties we cannot verify using CGAR. Let me just, okay, good. Now, I will try to convince you that maybe we should also look at some of those properties. So consider, for example, this long-running program, such as a command line application or a graphical user interface application, that basically has some main loop where we wait until the user presses a button, and then we perform some action, and then we loop again. Now, we might possibly introduce a bug where there is some infinite loop somewhere hidden in the program with some complicated prerequisites. So what kind of seems intuitive to me is to require that no matter where we are in the program, we can always, using some sequence of inputs, return to this label somehow. And this is actually formalizable as the CTL property AGEF label. And unfortunately, this property is not path universal. It says from every state we can eventually reach label with some sequence of inputs, and that is the existential quantifier on paths. This kind of property is usually called the recovery property. I also like to think about that as there is no loss of capability while executing the program, so we are still always capable to reach the label. And unfortunately, if we look at some path universal properties such as AF or AGF, these are not helpful here. For example, AF says that for all paths we can reach label in the future, but unfortunately we can on some path just have the button not pressed forever. So this property would be would not hold even without the bug, and would not be sensitive to it. Now, this kind of seems to me as a useful property that's not verifiable by CGAR, and our work on input-based TUR, using that we were actually able to find a bug in a real-life program. So let's first look at CGAR to appreciate why exactly we only can do path universal properties. So you might have seen this kind of control flow graph before, and basically what we do, we get a system and a path universal property. Then we generate an over-approximating Kripke structure which must contain all the paths in the original system, but it can contain also some more. And then we basically perform model checking on this over-approximating structure. If we get the result that the property holds in the over-approximating structure, we conclude it also holds in the system. But if we get the result it does not hold, we get a counterexample, which is a path, and we will replay it in the original system and see if it's valid or spurious. And if it's spurious, we will just refine and continue with the Kripke structure that's bigger and has more information. Now, obviously, the problem here is that we can only replay paths in the original system because that is just a concrete system without any abstraction. And fortunately, we also have another way of doing things, which is the so-called free-valued abstraction refinement, where this is basically done a bit differently, because instead of an over-approximating structure, we generate a so-called partial structure, which basically contains some information about the system, but potentially less. And then we perform free-valued model checking, which is very similar to standard model checking. And we get the result true, false, or the third value, which is unknown, where we see that from the partial structure we actually cannot determine whether the property holds or not. So we refine information and continue with the bigger structure. So this to me looks quite nice, and the question really is why this is not really used. Well, it turns out that the devil's quite in the details, because there have been a lot of TVAR frameworks introduced between 2001 and 2011. Unfortunately, they were quite theoretically and practically complicated. I will talk about it a bit more in detail. And basically after 2011, this kind of tapered out and everybody just used CGAR. So we have no practically used TVAR tools. Now, unfortunately, this gives us blind spots, not just in verification, but also in design, because if you cannot actually verify some property on a system that requires abstraction refinement to model check, why would you even consider this property when designing? So the question is, how can we improve on this? And what we did in our paper is we introduced a new TVAR framework that is simpler than the previous ones, implemented a tool based on it. This supports the whole ME calculus, and we found this bug in a real-life program. So let's look a bit deeper into this, and I will introduce this example system here, where basically this is just a simple finite state machine, which has states with 3 bits, and the labeling will be the most significant bit, so the leftmost one here. And we will want to be able to always recover to the most significant bit 0, so to these green states. Now, as we can see, this system is buggy, because if we go to the state 011, then we will reach the state 111, and then we will never recover to one of these green states again. So if we would feed this to a classic model checking algorithm, this is very simple, because we basically just discard all the inputs, and this gives us a Kripke structure. And this computes that AGEF MSB 0 does not hold. Unfortunately, this needs to really generate and consider all the states in the state space, and exponential explosions occurs very quickly. Now, if we look at how CGAR does things, CGAR actually approximates states by some abstract states. For example, here I will use the free-valued bit vector abstraction, where basically we don't just have bits represented by 0 or 1, but also by the third value x, which can be 0 or 1. And it over-approximates these states, but also transitions by so-called may transitions, which say that the transition may be there, but it doesn't definitely tell us something about its existence. And what we can see before, for example, we can start with the state that over-approximates every state. This will get a made transition to itself. And we can do splitting of states, where we say, okay, we will see states with the most significant bit 0, with the most significant bit 1. Unfortunately, of course, we need to add the main transitions where we need it to over-approximate. So, for example, from 0xx to itself, we need to have a main transition due to the transition, for example, in red, where we from 000 may transition to 001. Okay, so let's see how the previous TVAR frameworks resolve this problem, that we could not prove anything about the existential paths, and we needed to use counterexamples in CGAR. So Basically put, they introduced the so-called must transitions, which are usually drawn solid. And these state that all states within an abstract state must have a transition to some state within the successive abstract state. And if we do this, we actually get a very weird thing that we didn't get in CIGAR. And that is that before the refinement, where we just had the state XXX, we could use a must transition. We could see that this rel is there. Unfortunately, after splitting states, we cannot put a must transition anywhere from here. For example, for the transition in red, we cannot put a may transition there because we have in the state 0xx, we have the state 011, which goes only to the state 111, which is not in 0xx. So a very weird thing happens here that previously we could prove, for example, that some successor exists to the initial state. Unfortunately, after splitting, we no longer can do it. And this was recognized as a big problem in TVAR, and a lot of the literature deals with this, which is called non-monotonicity, that we can lose some provable properties after refinement. This is problematic, for example, because we can not really guide the refinement very well if we can lose some properties. And so monotone frameworks have been devised with more complicated structures, such as the generalized KMTS, where instead of just the must and may transitions, we have the must transitions, which can have multiple tails. They are hyper transitions. We have also mixed transition system, and this really becomes quite weird and complicated very quickly. But this is actually only necessary due to the fact that we split states. So let's try to do it a bit differently, as we do in the paper. And we will start with the notion of abstract simulation, where basically we will try to generate the abstract state space like this. We will start in the initial state, and we will say, okay, we do not care about the input. We will set it to X, and back in the automaton, we can see that we have the transition to 001 and to 011. So we can actually have an over-approximating state 0x1, and then we can do this successively until we get a lasso-shaped state space. And here, basically, we just have normal transitions. There is no problem with having multiple types of transitions, and this is quite nice. The main thing, obviously, is how to do the splitting. And since this is called input-based TVAR, we will split inputs instead of states. And the core idea here is basically that we know that we must consider all of the inputs. So if we just split the inputs, this means that we can leave the transitions as is, and we just have normal transition. For example, here we will just split the input X to 0 and 1. And right now we can actually, after generating the state space, we can see that AGEF, MSB0 does not hold any, and we could do this with less states than in classical model checking. So basically, with just the abstraction of the labelings and states, but without the abstract transitions, we can have the simple partial Kripke structure formalism. And there is basically no problem with monotonicity. Unfortunately, there's a problem that the abstract space may be unnecessarily big. For example, if we just want to compute that the most significant bit is 0 in the initial state, we still get this lasso-shaped state space, which may be very long. So what we did in the formalism was we allowed the decay of abstract states to more over approximate. So basically, after we compute this kind of abstract simulation, we can also say, okay, we will abstract it a little bit more, and here we can decay to XXX, and now we have just 2 states, and we have resolved this problem. Now, if we put this together, we can do refinements by input splitting and lessening this kind of introduced decay. And we can use existential abstraction, which is normal for the abstraction refinement in model checking. However, we can actually also quite nicely slot abstract interpretation to compute this abstract simulation. And in the paper, we have proven sufficient requirements for nice properties of the instantiations of the framework. And what really remains to make this work well is to choose the abstract domains and the refinements to make well in order to mitigate the exponential explosion. We have instantiated this in the tool Machine Check, which is freely available. And this is focused on automatic verification of digital systems, especially for machine code systems. And basically, we write the system descriptions in a strict subset of the Rust programming languages. We write the specification properties in Me calculus. And then Machine Check does explicit state model checking with the abstract states. And we currently support free-valued bit vector abstraction domain by default, and also others that are optional. We have evaluated this, and in the paper, we have verified some machine code programs for embedded systems for the 80 mega 328P microcontroller. And as I have said, we have found a bug in a program which is actually used in real life for voltage-controlled oscillator calibration. And what this does, it basically looks at the output of the oscillator, and based on whether the frequency is too low or too high, it does some kind of a binary search and trims the oscillator based on this. Unfortunately, the program contained a bug where basically the least significant bit of the trimming was not cleared. And this was quite sneaky compared to the trivial example of recovery properties, because this actually resulted in a loss of calibration accuracy, but it wasn't really obvious. I only found this bug after actually verifying a recovery property. And as we can see, the times are reasonable. We have also verified some properties that are not, for example, in the fairly simple computation tree logic, but just in the Me calculus. And there are some problems with the alternating quantifiers where the CPU times rises quite a bit, but this is just an implementation issue, not something related to the framework. Now, I'm currently working on this. For example, we have done a new RISC-V system implementation in December, and this can be extended. What I really am curious about right now, and what I'm trying to do, is to kind of transfer the ideas between set solving, SMT solving, and quantified Boolean formula solving, and model checking, because we see a lot of the time that CGAR tools are basically implemented using SAT, but we can also go another way around, where CGAR tools can solve SAT problems, TVAR tools can solve QBF problems, and we have a lot of parallels between abstraction refinement and DPLL or CDCL solvers. So I am actually looking at this. Seems quite interesting to me here. Now, in conclusion, we introduced a new abstraction refinement framework that's quite simple. It works in practice. Unfortunately, industrial usability is far away. And the last thing I would like to mention is that, of course, one of the things that's hampering the adoption of this is that currently we have just the verification benchmarks and competition that are focused on the path universal properties, for example, in software model checking. Now, however, now we can actually have the tools based on TVAR, and we can do much more. So hopefully this will go somewhere. Thank you.
Okay, thank you for the very nice talk. We have time for quite a few questions.
Yeah, so I was just wondering, so the problem with model checking is usually that if it's false, right, then you get a very detailed information, but if it's true, then you've just got like a thumbs up, right? So there has been some discussion about, like, can you produce some kind of certificate that, you know, some proof system or other?
So basically put I have thought about this a lot and basically put in the abstract state. Okay. The abstract state space by itself is basically a certificate for model checking, and basically so you have this thing, which for example in machine check you have a graphical user interface where you can look at this, whether this seems correct. And of course, you might be able to somehow, after you prove the property, somehow compact this. And for example, if you have just a path universal property and you find a counterexample, the resulting state space would basically be compressible to just the single path which contains the counterexample. So this to me seems that it is basically the proof object for this, and of course you could kind of translate it to some formal proof or something. This may be possible.
Okay, thank you.
Hi. Could you go back to page 15, I think, where you talk about abstraction of states?
Back or forward?
No, well, you abstract away in your approach. You abstract away states from.
Oh yeah.
How do you? Yeah. That's
Okay. Yeah.
No.
15.
15, I think, something like that. Yeah, exactly. So here you say, I think the idea is that from the initial state, rather than going to the next, like 0x1, right? Here you say you're trying to go to a more abstract state and we'll see what's happening. But isn't there a green transition within the XXX state, like in the original system? Like, isn't there not or
maybe I can go here.
Yeah. Okay. So from 001, there's a transition to 010.
Yeah. So
shouldn't that appear?
So basically, here from 000, there's a transition to 001 and to 011, and then we basically over-approximate that and say that there is a transition to 0x1.
Okay. Even here, that then so from x1x, I mean on the top part there's a transition, right? But there's a self loop. Why doesn't that appear as a? I mean, why is x1x gray? Because it's a mixed.
Oh, this is just basically that here the most significant bit is unknown. So the labeling of the most significant bit, which was here 0, this is unknown here.
Okay, so and I'll think about this, or maybe look at the papers.
And of course, this is just like the conceptual overview. Normally, you basically don't have this. You have some kind of description of the system, and you generate this from basically the description using just for example exact interpretation, where you go from you have some function that you interpret and you get this.
Okay. Thanks.
Okay, there's another question over there. I have a question regarding the evaluation. Can you go back to the evaluation slides?
Which do you mean?
I mean, where you check the properties of some real system, the recovery at the very end somewhere.
Yeah, experiments. Yeah.
So, first of all, what was like the size of the original system? So you only show the size after the refinement steps, right?
Well, the original system is a machine code program. So basically put you have like 2 to the power of 2048 initialized input, like in uninitialized memory cells that the program can use, although this one doesn't. And then you basically get to the power of 8 states in every kind of calibration. So basically, you could say it's at least 2 to the power of.
I mean, I understand. Okay, it's huge. It's huge. I understand.
It's just too big.
Okay, I see. Because I was wondering why, in so many cases here, you actually somehow reach the same number of states and transitions. So it
basically, this is quite. I would say quite nice. But what really happens here is that we actually kind of almost correctly go to the state space which kind of approximates the control flow graph with the things that we are interested in. So basically we get an abstract state space which kind of tracks the program counter in the machine code system, and then it also tracks basically what we are interested about. And yeah, so basically this was quite surprising to me that it went like this, because we, for example, have this inherent property where we check whether the instructions are actually correct, that there are no illegal instructions, and so on. And in the other properties, we actually here don't check this inherent property. So these only basically say, for example, if we can recover to some state with the calibration 0, and they don't care about illegal instructions at all. And still we get this kind of state space, which to me is quite nice.
Okay, thank you.
Okay, any more questions?
Thank you for the talk. The input-based splitting, right, was essentially like adding details back into the model to check, and then the decay was trying to like make it not explode. How much does the decay do compared to the input-based splitting? Like, how much does it help, and how much?
It really depends on the system. So, for example, we have some small systems which are not based on machine code, where the decay really helps. And for example, if you add an independent free-running counter to the system, then without decay, it basically explodes your system because there's some parallelism there that basically without the decay, you just need to take into account. However, you can say, okay, I will decay this, and I don't care about the free-running counter at all. And then you basically have no problem with this. Unfortunately, for the machine code systems that we have, and for the fairly simple strategies that we use for the refinement, it turned out that it's better not to use decay here. But I'm definitely looking at this, and basically, if we could have some better strategies for refining, then decay might be quite useful, because obviously the problem is that if you add too much decay, then you need to do many more refinements to actually find what is important and what is not. And so basically here, instead of naive model checking where you basically have just the state space size, here you also multiply that by the number of refinements. So it's kind of a trade-off between like having a big state space and doing refinements slowly but precisely.
Thank you.
Okay, some more questions? So I have a short question. So can you tell us about the bug you found? Have you reported it? Was it fixed?
Well, it was fixed because it was in my program that I did like 5 years previously to this. Okay. And well, it worked fine, but unfortunately, or maybe fortunately, I found a bug when I loaded it in here. Now, obviously, this was just in a very small embedded system that only did this voltage controlled oscillator calibration, but these kinds of very small programs are also found in some critical code, some very simple things like in your car you have a lot of these small embedded microcontrollers. Of course, if we improve on this, we might also verify some more interesting systems.
And what about the other programs? So this is all for the one program.
Yeah, this is just a sample. I also tried some different, maybe easier programs. I also tried a factorial program, which basically did factorial using recursion or iteration. It depends on how do you compile it, whether in release mode it actually can turn the recursion into iteration, and there we were able to, for example, find some stack properties that the stack doesn't overflow and so on, which is quite critical if you have a small microcontroller and don't have much of memory.
Okay, thank you. So that's all for this session. Let's thank Jan again. And speakers of the next session, please try your laptops and find your chair, who I think should be Borzo, who I don't see here.
Not for the recording. Okay, good morning, everybody. Welcome to the second session, morning session of the second day of VMCAI. My name is Borzo Bonakdarpur. I'm from Michigan State University. I'll be chairing this session. The first talk is multivariable quantification of BDDs in external memory using nested sweeping. And the talk is given by Stefan Solfsten.
Thank you very much. I thank all of you for also all the way over here. So science is said to be built on the shoulders of giants, and this little project is absolutely no different in that. For the first, I would actually like to start to go back all the way to 1986, where Randy Bryant published this paper, which until quite recently actually was the most cited paper in all of computer science, until the AI wave took over and then tons of citations then. And what the thing Randy did was say there's this idea of a binary decision diagram where you have a tree where nodes are merged like this. And every node here is then an if then else decision on some Boolean variable. So here we x0, if it's false, we go down here. If this variable is true, we go down here. And at the very bottom, we then also have all of these, the output of this Boolean function. So this is one way to represent Boolean formulae. And the idea that Randy had, building on top of this original definition by Lee and Akers, was to say, what if we have these variables occur in a specific order? So in this picture, it's always x0, then x1, then x2, and then x3. First of all, what we get out of that is, with a few extra tweaks in here and there, that this actually is going to be a canonical description of the Boolean formula. So if no matter how you write this Boolean formula, if it is functionally equivalent to another one, the BDDs will be structurally the same. So equality checking of Boolean formulae are very much trivial with binary decision diagrams. Another nice thing that comes out of having the ordering be fixed this way is that the algorithms themselves are very simple and to implement and to actually also analyze. And this gives us then also some really nice complexities in terms of the performance of this thing. So if you have a formula phi and some formula psi, and you want to compute the and, the or of this whole thing, you can do that purely in the time that is based on the size of the BDD, not actually the complexity of the formula. So you might have a very complex formula, but the BDD is teeny tiny, and because of that, your computation runs really fast. Of course, the BDD can also explode, become exponentially big, but, well, yeah, then you have troubles. But still, next to that, you can also assign a variable a single Boolean value that will also be an operation that will only depend on the size of the BDD, not actually the complexity of your formula. If you combine these things, you can also do the existential quantification, because that is essentially just the same as assigning false, assigning true, and doing the OR of these two. And because combining these two things, we then also can do that in quadratic time, based on the size of the BDD. Now, this was really big back in the 90s. Then SAT solvers came in, kind of took all of the glory, with very good reason. They are doing a really good job with that. But there are still some use cases where binary decision diagrams are useful, both from just regular model checking, but probabilistic model checking still sees very heavy use of BDDs nowadays. Quantum is on the rise, and analyzing quantum algorithms on a regular machine, binary decision diagrams are kind of finding their way to as a representation of the matrices. And also they're finding their way as the explainability of AI algorithms nowadays. So they kind of like also have a resurgence this way. But the usual way you're implementing this is by doing recursion. This is a nice recursive structure. Let's not redo computations all the time, so let's do some memorization. So that's a hash map. Let's not recreate the same node several times. So let's also have another hash map for that. So hash maps, and recursion. That's a lot of jumping around in memory, which isn't really the best in terms of how our computers actually work. So if we go all the way forward or backwards to 1996, Lars Age just finished his PhD in Aarhus and began to look at one of the first things he wanted to look at in terms of I/O, later finding lots of other places where he had a high impact on the design of practical and theoretical algorithms for with respect to like optimizing how the I/Os work. Let me try rephrase that. So he ended up being a very big person within the area of I/O efficiency. I/O efficiency is the idea of trying to make an algorithm that actually has optimal reads and writes on the data. And so one of the first few things that he actually began looking at was binary decision diagrams and how can we actually optimize the behavior of these. And one of the things he proved was if you use depth-first recursion and you use memorization tables, you will asymptotically, in theory, have bad behavior. And you can also see that in practice nowadays. There was a paper relatively recently by Pastva and Hensinger, which essentially proved that our CPUs are getting faster, but they're also getting faster compared to the RAM. So the RAM is now slower compared to the CPU. So actually, the speed of BDDs are actually slowing down nowadays compared to the CPU time, because we are not actually properly dealing with cache misses. But he also proposed a different way of actually computing on binary decision diagrams. So what he proposed was to say, what if we have this BDD operation? It could be the AND, the OR, the exist. Let's split it up in two different parts. First, we have the apply phase, and then we have the reduce phase. So if we want to do an existential quantification, we have one formula and one variable as an input. We're going to have some transposed output in between, and then we're going to be cleaning up a few things afterwards. The way this kind of then looks is if we have a BDD like this. Let's quantify out the first variable here, x1 variable, sorry. And so we're going to be doing this by going through the whole thing, sweeping level by level. And so slowly we build by level the output. X1 would then be turned into an OR node, and then we continue the computation all the way down like this until we have final output. What is interesting about this way of doing it is, first of all, how is the input laid out in memory? We make sure that it actually is laid out level by level, so meaning that we have, by having computed it this way, we've also been following the order in which the input was laid out in memory. So we've just been sequentially reading through the input, and sequentially reading through the input is I/O efficient, so that's great. But how did we then actually deal with all of these recursions? Because these recursions were also jumping around inside of memory. So instead of using a stack to deal with the recursions, we're going to be using a priority queue instead. And this priority queue is then taking your recursions and then sorting them to match the order in which you're going to be reading the input. And so essentially what you have here on the right is the recursion tree unfolded into a diagram like this. And the priority queue also actually is able to merge recursions to the same target together. So it also is doing double duty as the memorization cache. So if anyone was worried about this exploding this thing in between, this tree is the same size as you would do the one you would be traversing in your normal recursion, except for the fact that you're now actually outputting the whole thing. But as you can also see here on the lower right, we're also creating some nodes that need to be reduced. Essentially, at this point, we have been simulating the recursion down, but we haven't been simulating the return of the recursion at this point. So that's going to be the next step, the reduce. So we're going to start from the bottom. Luckily, some of you might have noticed these edges were already reversed. That was, let's not go into much detail, but that was because the way we outputted the whole thing previously, nicely everything then just ended up being transposed, which is lucky for us because we need to know the parents to actually return to them. So again, reading through the whole thing sequentially, which is just running through the output backwards. That's the same as going back up again. We can then also have a priority queue sending information to our parents. And so we end up creating the final output. This is essentially all you need to know about how these algorithms worked. Everything else is magic. So how does this look how is the complexity of this thing then? Well, similar to before, we might have a formula phi and psi. We want to compute the AND and the OR of this. And now we have this kind of looking the same thing, but slightly different. So it's the sort of these two formulae. It's the sorting complexity, which usually in the time is like going from n to n log n. So we add a logarithmic factor on top of it. But in the I/O model, the sorting is also an n log n thingy, but random access is exponential. So it is some way heavy improvement, going from exponential down to an n log n. So we're paying a little bit of a cost asymptotically in the running time, but we're gaining a lot in the I/O complexity instead. You can also apply the same idea to then assign a variable, a single value. Again, you get an n log n kind of thing, but have a heavy improvement on the I/Os. And combining this again, you can also do quantification of a single variable by combining these two steps into a single algorithm, again for quadratic complexity with a small logarithm on top of it. And if you can quantify one variable, you can also quantify k variables. Every time it might grow twice as large and double in size, so you kind of get this exponential increase in the size, which is also equivalent to what you're seeing in the asymptotic complexity of the depth first version. So it is essentially running asymptotically as we would hope for in most cases. So if we now go all the way over to 2022, I, together with a few others, we dusted off this paper by Lars Age and actually implemented it in practice in a tool called Arger, which, given all of these algorithms and building on top of a library that actually implements I/O-efficient priority queues, I/O-efficient reading and writing of files, and sorting algorithms, gives you the ability to actually compute on binary decision diagrams that are way, way larger than the RAM of your machine. So we ran, and also we're later going to be seeing benchmarks, algorithms running on a computer with like 300-ish gigabytes of memory. And we were dealing with binary decision diagrams of 700, 800, 900 gigabytes in memory, or gigabytes in size. And the performance was essentially not changed. It was as fast as the smaller ones. You didn't pay the cost of going to the disk, whereas if you're going to use a recursive implementation, you're going to be using swap memory, and then you're going to have several orders of magnitude performance decrease. So for large binary decision diagram manipulation, this will work really nicely. But until now, at least, we've always been quantifying. If we what I've showed you previously was essentially also the way we're doing it in here, not the original way that Lars Age actually proposed to do it. He did it a little bit more complex because he was mainly just interested in the asymptotic complexity. So in part of this work was also just cleaning the whole thing up, simplifying it, optimizing it, making it run faster, and also both on paper and in practice, mainly in practice, not asymptotically. But at this point, we've only been quantifying one variable at a time. And so that kind of sounds like something that would be really bad if we want to do model checking and things like that. And usually the way that conventional depth-first ways of implementing binary decision diagrams do it is by actually having a nested recursion inside of the algorithm. So question is, can we somehow recreate the same thing in our implementation? If we want to quantify multiple variables, can we somehow have a nested operation so we're not dealing with creating stuff and touching stuff that we don't need to do? So that brings us to this year with this paper, where we then are proposing the idea of using nested sweeping. So if we take this previous picture with the apply-reduce tandem we had, we're going to wrap it in a second apply-reduce. So first of all, we have one apply phase, which just is going to do some computation. We can try and alter this a little bit, but it actually doesn't matter what this one is going to be doing. Let's just simplify things and just assume this doesn't do anything except reversing the edges back up again. So we know the parents. So we're essentially just transposing the input. But by transposing the input, we can start from the bottom and go up. So we get it as the second animation you saw. And so part of the reduce, we now know all of the variables we want to quantify. So we're going back up until we find some variable we want to quantify. We are not touching anything above this, so we are skipping some work here. And now we're going to start a nested apply-reduce phase down here until we're back up here, and now we can continue. Which kind of, again, now is the idea is that this simulates the way that the conventional depth-first implementations also would go down, recurse, and do something nested down here, and then return. So the animation look would then look a little bit like this. On the input on the left, I've already kind of transposed the inputs. So the edges point upwards. And now we're going to be creating this output here on the over on the right. Since this is already fully reduced, there's nothing really that happens. There's nothing much interesting going on in the beginning. We're just recreating the input essentially. But we can also do something else interesting on the input prior to that, but let's again ignore that. But at some point, we're going to get up to one variable we want to quantify. In this example, I want to quantify x0 and x1. And so now we want to do a nested OR operation on this forest of I have beneath. So let's here in the middle actually do a nested operation on this entire forest, starting from the edges we have from the input that goes down into the original forest and also in here. So, and recording on the output also how this connects back, how this connects back into the original input. So we go down, and similar to what you saw in the animation you saw previously, we're going to create this intermediate output where this node needs to be removed. And so now this output, this whole thing has done its work. We can just delete that file from the disk, and we create a new output. So, and now again, we can then go back up again with that, create the reduced output this way. And now this essentially, while going up here, we are overlaying this on top of that one to create the new version of the thing that we need to have reduced. And these gray edges are then used to connect this new version back into the original one. So we're going all the way back up here. X0 is also a variable we want to quantify, so that one is also going to, again, be seen as an OR node and spawning recursions that for going back down again. So let's again remove the thing in the middle. We don't need that one anymore. And then start here again from and going back down. We create the product of these two variables, nodes, and then also this x3 node, and then also the leaves at the end. Reducing this one is not that interesting. It's already kind of reduced. And so we have the final output. Asymptotically speaking, did we win anything? No. So still, if you have a formula and you have k variables you want to quantify, it's still going to be taking this exponential possible time. But that is also just because the binary decision diagram might explode. So there's asymptotically not any win. But as I mentioned previously, we're going up to some level, and then we're doing some work down here, never touching anything above. So we would assume at least that there should be some performance increase in practice, similar to why you're doing this whole thing, also kind of doing this whole thing in the conventional implementations. Yes, I'm good on time. So let's actually look at things in practice. For that, we have two benchmarks. First of all, we have a Garden of Eden question of, like, given a grid of size n1 by n2, in this case in Conway's game of life, does there actually exist some some initial state that doesn't have a predecessor? So is this a initial state that is not reachable in any different way? So this is a problem that is very close to being a relational product, but without you wanting to use the relational product. So that is really nice in our case, because we want to test the existential quantification without having to deal suddenly with tons of different extra issues of how can we do something with the relational product. Next up, we also have also tried out with quantified Boolean formulae. So you're given a formula with some exist for all and so on, with the quantifiers alternating until we find some matrix, some formula that depends on these variables. And specifically for inputs, QBF formulae that we're going to be using are like two-player encodings of two-player games, like Hex and the like, based from Scheik and Van de Poel. The reason we're going to be taking these in particular is because, based on our experience, these symbolic encodings actually work really well for binary decision diagrams. So this is a reasonable use case for actually using this data structure. So in orange, Garden of Eden, in blue, quantified Boolean formulae. So first of all, how well do we actually improve performance of our implementation? if you ignore these few dots here that are 5% performance decrease, in general, just the bigger things get, the more we get out of this. On average, we got an performance increase of like factor 1.7. I should have mentioned, yeah. So here on the x-axis, sorry. Here on the x-axis, we have the running time without the nested sweeping. And on the y-axis, you have the speed up gain. Sorry about that. So above the line would be speed up, and below the line, slow down. Okay. Next time, axis first. Let's talk about the axis first. Next up, we wanted to compare with another BDD package called CAL, back from the 90s, which is the only other BDD package, as far as we know at least, that tried to actually do binary decision diagrams on the disk. The way they did it was still using hash tables, then a hash table for every level, and then did breadth-first algorithms to try and be a better dealing with that. And the IOs to the disk was just dealt with by swap memory using the operating system. And here there's a kind of an interesting thing happening over here on the left, but let's start with the things on the right. So essentially, we are just winning by several orders of magnitude. Here on the x-axis, you have the running time for our algorithm, so the complexity of the whole thing. On the y-axis, you have the relative running time of CAL. And we are, in many cases, like several orders of magnitude, like 1,000 times faster than CAL. Pretty much all the way across the board. You have some X's on this plot. This is literally just because we underestimated how slow CAL was going to be compared to us. And for every instance, we had to actually note down how much time this specific instance was going to get, because if we gave everything 15 days, the scheduler would not be happy about us. So we had to somehow gauge how much it would be. So all of these X's are worse than their placement. Then you might be wondering about what is happening over here. CAL is actually kind of cheating. So for smaller instances, it actually uses depth-first recursion. And as far as we can tell, this is probably pretty much right around here that it actually is switching over from the depth-first recursion to the breadth-first algorithms. So at least in terms of like actually using the disk, we are at least right now it seems to be the fastest implementation. So that's also the goal. So that's really nice. But what about how well do we do against depth-first implementations, the ones you would actually usually be using? First of all, these benchmarks are run on computers with 300 gigabytes of memory. This is primarily just to make the depth-first implementations able to survive for long enough, and because we don't want them to actually throttle on memory in any way. And we've also set up a lot of different other settings in these things in their favor. So just to be sure before I show anything to you, we are essentially giving them every other implementation as much benefit as possible, except for the fact that the multi-threaded versions are also only given a single core. But other than that, it's very much in their favor. So we have in the paper, we have compared with 5 different implementations. Here I've just taken 2 that you probably would know. So Buddy from Copenhagen and CODD from Colorado. And Buddy has probably the clearest picture of how performance essentially goes when you want to compare. So again, below 1 second, we have an interesting area where the performance of our priority queues and reading and writing actual BDDs, tiny BDDs to files on the disk is just a major overhead, and you shouldn't do that. And so we are several orders of magnitude slower than this implementation, which is fair enough. It's out of our scope. It's not what we're trying to do, at least right now. And then, but at some point, at least our priority queue and files kind of stabilize on the overhead. And we stabilize around a factor of 4 performance slowdown of using Argia over a depth-first recursion. But again, remember, like we have been given as much favor to the depth-first recursions implementations. So this is very much like a worst case performance decrease, hopefully. But then at some point, after having been through these small instances, these medium instances, then we get to the large instances. And here Buddy is suddenly just crashing in performance. And this is because it's running out of memory. It does so quite early because it only uses 32-bit integers. But because it runs out of memory, it tries to like do garbage collection, and that is slow by itself. But also garbage collecting is going to clear out the memorization hash tables, which means it is going to recompute on previous operations already. So it's both doing slow garbage collection and suddenly now recomputing quite a few things. And so suddenly it spikes in performance until it just completely gives out either with a memory out or a timeout. Timeout essentially just being, it's repeatedly garbage collecting, so essentially the same thing. And for CODD, it's kind of the same picture, but a bit more muddy. At least for things that are, for small BDDs, we are completely crashing in terms of performance, but at some point it kind of stabilizes, and we are winning for larger instances. And with that, we can kind of like say that with nested sweeping, we have been able to actually take these results we had from 2022, where we had also had a 4-factor decrease in performance, and we've been able to translate it over to these more complex operations like like the existential and the quantification. So in general, this is just a framework you can actually apply to simulate any BDD algorithm that recurses more than just once. So you can do quantification. We also have the relational product since then implemented. You can also use this for functional composition. And if someone is interested, my PhD thesis is also providing you a pretty novel way of doing variable reordering based on this approach. All of which should be able to actually deal with binary decision diagrams way larger than the RAM of your machine. It also, having nested sweeping and supporting multi-recursion that way, also kind of gives you the ability to implement and support other types of decision diagrams, such as decision diagrams for quantum and for cryptography. And all of this just dealing with binary decision diagrams that otherwise is completely beyond the memory capabilities of your machine. Thank you.
Okay, we have time for a couple of quick questions.
Thank you for the talk. I would like to know, did you use solid-state drives or regular disk-platter hard drives for the evaluation?
The evaluation was on an SSD, yes. So it was only 100 times decrease in performance if you were using swap memory for like the first implementations rather than a factor of 1,000, roughly speaking. And
do you think the algorithm would be highly impacted by like having disk-platter drives with just sequential read, or would it scale nicely?
You can do a few things to make it scale more nicely, but yes, you're going to be slightly impacted by the disk. But I'm also would emphasize slightly. So maybe you would have a factor of 2 decrease rather than a factor of 10 or factor of 100 decrease in performance. Also, the way, not going too much into the I/O model, but the idea is instead of just reading a single page or something, you're reading in a bigger block of memory. By default, that block size is set to 2 megabytes. You could increase that to 16 megabytes, and by that you're also you're more dealing with or bridging this gap of problems. Reading from a hard disk, the expensive part is not reading the thing; it's seeking the thing. So the bigger things you are reading, the better it is.
Okay, thank you.
Yeah, thank you for the talk. I was wondering, your algorithm always goes to disk, right? So yes. No matter how small the BDD. So intuitively, I would assume that maybe the sweeping-based approach is even better also in RAM because it utilizes the cache better, like in comparison to the recursive approach. Do you have an idea if this is true? Like if you stay totally in RAM but still replace recursion by the sweeping?
I have not tried to say, I mean, the whole thing has been set up quite modularly, so you could do that, but I haven't done that. But you could try and see if you could like replace files with internal memory vectors and replace the priority queue with like a cache optimized internal memory priority queue. Then you would probably get quite a bit of a performance increase, yes. But I have no practical evaluation to back it up.
Okay, thank you.
Okay, I do have one question, but I'll ask you after the session in the interest of time. Okay, let's thank Stefan again one more time. Okay, the next talk is producing shorter congruence closure proofs in a state-of-the-art SMT solver. And the talk is given by Bruno Andriotti.
Right, thank you. So equality reasoning is a very essential part of modern SMT solvers. It's, of course, useful for the theory of equality and uninterpreted functions, but it's also heavily used internally in other theories. And this is usually done using what we call a congruence closure algorithm, which allows the solver to determine equivalences between different terms. So for SMT solvers, however, it's usually not sufficient to just say whether two terms are equivalent. So we might also be interested in an explanation of why they are equivalent. So for our cases, an explanation here is just a minimal subset of the input literals that is sufficient to make the terms equivalent. So you might want this, for instance, if you have a proof-producing SMT solver. So if you're making a proof for the entire problem, a part of that proof is going to be equality reasoning, so you need an explanation for that. But also these explanations are used for conflict clauses in the SAT solver, which kind of guides the search through the problem. And ideally, of course, we want these explanations to be small, right? So if you are producing a proof in the end, then a small explanation will result in a smaller proof, which is easier to check and reason about and all that. And also, the explanations, when they are used as conflict clauses, well, a small conflict clause will prune a larger part of the search space. So that can actually speed up the search of the solver as a whole, which is quite interesting. However, we have a theoretical result that shows that finding the minimum explanation for a given congruence closure problem is NP hard. But nonetheless, we can try. And a few years ago at VMCAI, Oliver Flatt and collaborators, they presented a new algorithm for congruence closure, which can demonstrably produce shorter explanations. And their work was in the context of an equality saturation tool, which is called the EGG. And while that is very interesting and complicated on its own, we are interested here in SMT solvers. And they offer a few different challenges from equality saturation. So for one, we have backtracking. So the solver can assert a few equalities and then go back, so we have to deal with that. And we also have to interact with different parts of the reasoning of the solver, right? Different theories or the SAT solver as a whole, things like that. So the main contributions of our work here, so we modified the Oliver Flatt's greedy algorithm to work in the CDCLT algorithm that is used in SMT solvers. We implemented this approach in CVC5, which is a modern, industry standard, not standard, but like industry strength SMT solver. And we also did a quite extensive experimental evaluation to see if this implementation is worth it or not. So more formally, we can say that the property of congruence states that if you have two sets of terms and we have a function, an arbitrary function applied to those terms, we say that the function applications are equal if the arguments are pairwise equal. So more concretely, if you have, for instance, if A equals B, we can derive that f of A equals f of B for any arbitrary function f. Additionally, we can define that for a given set of equalities, we say that their congruence closure is the minimal equivalence relation that satisfies these equalities and is also closed under this congruence property. Traditional algorithms for finding congruence closure, they are based on a union find data structure, and they construct a graph which we call the equality graph, or the E graph, which represents the equivalence relation that we're going to be building. And once we have that graph, finding an explanation amounts to simply finding a path between the two terms in the graph. So let's, and looking more detailedly at this graph, so each term in the problem will become a node in the graph. And the graph is going to have two types of edges. The equality edges, they correspond directly to the input equalities given to the congruence closure. And we're also going to have congruence edges, which they represent an equivalence that we derived via congruence. So a congruence edge, it's going to have what we call a justification. So the justification for a congruence edge between two function applications is going to be the set of pairs of terms that are the arguments of these applications. So in a sense, the justification is like the pairs of terms that have to be equivalent in order for the edge to be valid. So let's look at an example here. So we have a bunch of terms, and we're going to be adding equalities to the graph and seeing how we can construct this E graph. So for instance, if we add the equality x equals y, we're going to add here an equality edge between x and y, which we're denoting with a simple line. But we're also going to add a congruence edge between g of x and g of y, which is this double line here. And here we're going to say that the justification of this congruence edge is the terms x and y. So we can continue. Let's say we add y equals z, which adds another equality edge. So when we add, for instance, z equals w, now we know that the terms x and w are equivalent. So we can also add this other congruence edge between f of x and f of w. So let's say we add the equality x equals z. So this equality is in some sense useless to us because we already know that x and z are in the same equivalence class. So we just ignore it and continue. And we go on like this. So v equals u of y, f of w equals u of x, blah, blah, blah. And let's say at the end, OK, so here we have another useless equality, right? F of w equals v. So we already know that v and f of w are in the same equivalence class. So again, we ignore it. And let's say at the end, we add u equals f of x, which causes the congruence edge between f of u and f of v to be added. So let's say we want the explanation for the equivalence between f of u and f of v. How would that work? So like I said, we first find the path between them in the graph, which is going to be just this edge. There's an edge between them. However, since this is a congruence edge, we also need its justification to be valid. So we also have to find an explanation for each pair of terms in the justification of this edge. In this case, the justification is just the terms u and v. So we have to find a path between u and v, which is quite simple. It's this one. But now again, we have two more congruence edges that we need to explain. So we, again, recursively explain the justification of these edges. So let's say we start from this edge here on the right. We have to explain that x equals y, which is just this path here. And then for the other congruence edge we missed, we have to explain that x equals w, which is going to be this. So at the end, we have this E-graph. And the explanation was for the equivalence between f of u and f of v was just the entire graph, right? So every equality that we added to the graph was needed to explain this equivalence. Right. So you might have noticed that we discarded some of the equalities that were between terms that we already knew were equivalent. And that was not an accident, right? So you might think that we can use these equalities to allow us to find a shortcut in the graph, or allow us to find a shorter explanation between two terms, and thus a shorter proof. And that's exactly what Flat's greedy algorithm tries to do. So it makes use of these redundant equalities to find these shortcuts in the graph. So let's go over again the example. So everything starts the same, so x of y, blah, blah, blah. But once we have this z x equals z equality, which was redundant, we don't discard it. So we add it to the graph using this dashed line here, which represents a redundant edge. So we continue. Later on, we have another redundant edge here between f of w and v, which we add again, and so on. And then at the end, we're trying to find the explanation for f of u and f of v. So it starts out the same. We find a path between them. However, now, when we want to explain the equivalence between u and v, well, we have two paths to choose from. So, you know, we have a little bit more freedom here. So let's choose the new path, right? The one that uses the redundant edge. And now, as you see, there's only one congruence edge in this path, which we need to explain as well, which is between x and w. And again, we have two different paths between x and w, so we can choose. So let's again choose the new one. And this is the final explanation for the equivalence between f of u and f of v. So as you see, this is quite a bit smaller than the previous explanation. So keeping these redundant edges allows us to find these shortcuts and, you know, get a smaller explanation, at least in theory. However, one thing you might have noticed is that now that we have these redundant equalities, the graph for each equivalence class is no longer a tree. So it can be just a graph in general. Which means that while before there was a unique path between any two terms in the graph, now there can be multiple paths. So how can we select which path to use to find an explanation? So that's exactly what the greedy algorithm tries to do. So it does that by first assigning a weight to each congruence edge. And we see how these weights are calculated. But they are defined to be the size of the explanation for their edge, or at least an estimate for the size of the explanation to for that edge, as is returned by the traditional congruence closure algorithm, which is without using redundant edges. So basically, we call the old traditional algorithm for every congruence edge to find an estimate for its size and use that as the weight. And then, so here's the algorithm for doing that, right? So it's very simple. So at the start, the weights is infinite for everything. But for every edge, which is a congruence edge, we call the classical explanation here and get its size. And for equality edges, the weight is just 1. Right. So once we have the weights computed for the graph, to explain the equivalence of two terms, you know, we just find the shortest path between them using those estimates as weights. And of course, again, we're going to recurse on congruence edges every time we find them. However, there's a little added caveat here, is that we don't do this recursion forever. So we only go into a certain depth, which is determined by a fill parameter, and we'll see how this works a little bit in the pseudocode. Right. So here the first thing is, so when the fuel is 0, so if you have ran out of fuel, we are going to use the classical explanation again. So the reason for this fuel thing is because this explanation algorithm is slower than the traditional algorithm and has a worse complexity. And in order to like keep things more efficient, we have this few which basically uses the algorithm only up to a certain depth. And then if the explanation is too deep, we just give up and just use the classical algorithm, which has a better complexity. But in the general case, what we do is we find the shortest path between the two terms. This just using like Dijkstra algorithm or something. And then for every edge in that path, if it's just an equality edge, we add it to the explanation. But if it's a congruence edge, we go through its justification and explain everything recursively. Of course, decrementing the few. Right. So the way I described it until now, this algorithm kind of depends on the input having enough redundant equalities so we can find shorter paths and can actually have an improvement in the explanation size. So that's not ideal. So on top of that, we also compute extra redundant edges to kind of maximize our chances of getting a shortcut in the graph. And the way this is done is we find terms that are in the same equivalence class that have the same canonical form. So the canonical form of a term is defined as if you have a function application, you're going to take each of the arguments and you're going to take the representative of the equivalence class of that argument and you're going to apply a function to that. So in a sense, the canonical form of a term, should I say, if two terms have the same canonical form, it means that they are directly equal because of congruence. So we can add a congruence edge between them. Here is the code for computing these extra edges. So we keep a data structure which maps a congruence form term, a canonical form term, into a set of terms that has that as their canonical form. And for every term in the equivalence class, we find every other term which has that, the same canonical form, and we add an edge. However, do notice that we only do this up to a limit. And the reason for that is because this algorithm, in theory, it might add edges, a quadratic number of congruence edges in relation to the input problem, which is very bad for performance. So we only do this up to a limit. Right, I mentioned, talk a little bit about this later, but this limit is usually a linear multiple of the number of total edges. So we keep the number of edges in the graph linear with regards to the number of nodes. Right, so this algorithm, as described, works great for the application it was developed for, which is EGG, this equality saturation tool. However, when we are adapting this algorithm to an SMT solver, there are quite a few interesting, or should I say annoying challenges, right? So for instance, okay, I thought I had it on the slide, whatever. But so I'm gonna go over quickly some of the challenges that we had, but there were many, so I'll try to be quick. But the first one was dealing with backtracking. So as you know, SMT solvers, they try partial solutions, and when they determine that one solution is invalid, they have to backtrack to a previous state. So our algorithm has to be able to efficiently revert the state back to a previous point. So the way we do this is, well, the first thing we have to do is that we have to lazily compute the weights for the greedy algorithm, so we don't do extra work that we are not going to need. But also when we backtrack, we have to clear the computed weights that have become invalid. So we have to safely determine which weights are invalid and which weights we can keep when we're backtracking, which is a bit tricky. So another annoying thing is the limitation on the number of congruence edges. So by default, the greedy algorithm limits the number of edges such that at any point in the graph, the total number of congruence edges is less than half of all edges. However, this is not enough for SMT solvers, because an issue we had, for instance, is when at a certain point the solver adds an equality and then creates a bunch of congruence edges and then backtracks and then adds another equality and then creates a bunch of edges and backtracks again. So in a sense, we're kind of doing a lot of work and adding a lot of edges that we're not going to use. So what we had to do is to limit the total number of edges which are added kind of historically throughout the whole run of the solver and not just at any point in the graph, which is a bit more complicated. But in general, like the biggest challenge we had was dealing with the implicit dependencies that the eGraph has with other parts of the SMT solver. So when we were discarding the redundant equalities, we could never have any circular proof in the solver. And that is because once we add a congruence edge, the path between the terms in its justification is fixed in place. It can never change. However, this is no longer true because we can add a redundant edge afterwards in that path and add a shortcut. But this can create a problem when the congruence closure engine is interacting with other parts of the solver. So for example, let's say the set solver asserts a bunch of equalities into the congruence closure, A equals B, C equals D, and B equals C. So at that point, we can derive by congruence that f of A equals f of D. So the congruence closure engine is going to do that, and it's going to return that information into the SAT solver. So let's say then that the set solver, for whatever reason, maybe it has a clause that does this, or maybe there was some theory reasoning that does this, but let's say it derives A equals D, based on this f of A equals f of D equality. So it's going to derive that, it's going to send that to the congruence closure engine because it is an equality. And at this point, we're going to add that as a redundant edge, right? Because we didn't have this equality before, but we already knew that these two terms are equal. So what happens now when the set solver asks the congruence closure engine for an explanation of f of A equivalent to f of D? So if you think about the E-graph that we would have constructed in this situation, it would look something like this. So here on the bottom, we have the three asserted equalities. And on the top, we have the congruence edge that we added. And the dashed line here is the redundant edge that was added later. So when explaining f of A equals f of D, it would be very tempting for the algorithm, and it's probably what it's going to do. It's going to find the path between A and D that uses the redundant edge directly, because that's probably shorter than the other three edges. However, if it did that, what's happening is that the set solver derived the A equals D equality based on the f of A equals f of D equality that the congruence closure gave it, while the congruence closure engine is now saying that the f of A equals f of D equality is explained directly by the A equals D equality. So we have, in a sense, a circular proof, right? So the two parts of the solver are saying that one thing depends on the other in a different way. So that's a very tricky problem to solve, and we tried many different solutions to address this. But at the end, the solution we found that was simpler and easy to implement and that actually could solve this problem was what we call the level system. So we have augmented the equality graph to add an edge level to each edge in the graph. And in this case, this edge is just the number of edges that exist. This level is just the number of edges that existed in the graph prior to that edge being added. So in a sense, it's just like an incremental counter. So each edge is numbered. And when we're explaining a congruence between two terms, we can only use edges which were added before these two terms were known to be equal. So for example, let's say we have this, so this is the previous E-graph, but now we have the edge levels added. So as you can see, so the first three equalities have level 0, 1, and 2 in the order they were added. And then the congruence edge has level 3 because we discovered that it was equal after that. But now the redundant edge has level 4. So when we are explaining the congruence edge between f of A and f of D, we cannot use the redundant edge because it has level 4, which is greater than the level of the equivalence. So this approach fixes perfectly the correctness of issue that we had before. However, it is also quite restrictive in how we can use redundant edges in the proof. So, this is a problem as we see in the evaluation section, but we think that maybe a different architecture of the set solver can maybe allow more flexible solutions, because this is kind of like deeply linked into how the set solver keeps the asserted literals. So let's follow on to the evaluation, right? So to evaluate this implementation, we ran on a very large set of problems from SNTLib. And we were focused on the theories of EUF, of course, because it involves a lot of equality, but also on the theories of strings and arrays, because they are big, complicated theories that also use equality reasoning internally. And also the theory of linear arithmetic, mostly because if you're going to use arrays, you're going to need linear arithmetic usually. So we split the analysis into basically these three groups. So we have the theories which are based on arrays, based on strings, and all of the remaining logics. And we focus our evaluation on just the impact of that greedy had compared to the traditional algorithm as it was implemented in CVC5, which we refer to as vanilla. So this is a summary of our results. So as you can see, the impact on runtime is quite significant, and there are many reasons for that. So we are increasing the number of edges, which kind of increases the graph as a whole. Also, the path finding algorithm is much slower than just finding the unique path between two terms in a tree. However, that runtime comes at the benefit, at least, of having a smaller proof. So we were able to find a very consistent reduction in proof size of about 3%, which is not very impressive, but you have to understand that this proof size is the proof at the end of the solver. So it's going to involve other types of reasoning, it's going to involve other theories, and also it might not include all of the explanations that we computed. So we also measured the local explanation size. So for every call to get explanation, we measured the size of the explanation returned and added all that up. And as you can see, this is very theory dependent, right? So for the logics which don't have either arrays or theory or strings, the reduction was quite big, more than 20%. But for strings, for instance, it was less than 1%. So as you can see, these theories use congruence closure engines in very different ways. But on average, we had around an 8% reduction in the local explanation size, which is quite a positive result in our opinion. So this is a scatter plot of the runtime separated by each of these theory groups. And what's interesting here, so you can see that in general, there are more dots above the line. So the axis here, so on the x-axis we have the runtime for vanilla in milliseconds. And on the y-axis we have the runtime for greedy. And the 10 here is because we're using a fuel value of 10. So we also tested out different fuel values, but they didn't make much of a difference. So as you can see from all of the three theory groups, we have more dots above the line, which means that greedy was slower, especially for very large benchmarks. So for instance, for strings, you can see that there's certainly some degenerate behavior here, where the very large benchmarks, they take quite a long while to solve in greedy. But the interesting thing is that there are a few benchmarks which are faster to solve in greedy. Especially for the arrays theory, there is this weird cluster of benchmarks which took a few seconds to solve using the traditional vanilla algorithm, but took only a few milliseconds to solve using greedy, which is quite an interesting result, right? And the reason we think this is happening is because, like I said in the beginning, smaller explanations can result in a smaller conflict clause given to the SAT solver, which in turn can speed up the SAT search. And apparently in some cases, especially for the arrays theory, that can make quite a big difference. So additionally, we also measured how heavily the redundant edges we added are actually used in explanations. This is kind of to infer how the level system is restricting this. And we saw that for all of the returned explanations, the average number of redundant literals in the explanation is 3.5%, which is not a lot, especially considering that, so it's also heavily theory dependent as well. So like I said, strings, it sucks for some reason. But this is not a lot, especially considering that on average for the whole E-graph, around 40% of the edges were redundant. So this really indicates that the level system, while it is necessary to fix the correctness issue, it does include some problems in being too restrictive with which edges are used. So in conclusion, I hope I was able to convince you that this kind of approach that uses redundant edges has promise to be efficient in an SMT solver. So while these techniques, they have a quite measurable impact on the explanation and proof size, they do come at a significant increase in runtime, though sometimes it can also improve runtime for some exceptions. And another interesting conclusion is that despite having many redundant edges in the graph, they're not heavily used in the returned explanations. So for future work, we really want to try as a priority to improve the runtime performance of this. So this can be done just by better optimization of the implementation, which I'm sure there's a lot of work to do there, but also smarter heuristics on how we search for a path in the graph. We also want to develop new heuristics for computing the edge weights. So one interesting idea, for instance, is to take into account the SAT level of the edge literal. So for instance, if you have a literal which was asserted at a very old level in the SAT solver, it might be interesting to have a lower weight to prioritize using that literal in the explanation, because that literal will correspond to a larger section of the search space, and you can speed up SAT search even more. We also want to explore how we might address the implicit dependencies issue beyond the level system. So like I mentioned briefly, this level system is kind of deeply related to the way that the SAT solver stores the literals in the trail. So we don't think that there is a current alternative solution that would work with the way that SAT solvers currently work in CVC5. However, there is some interesting work, for instance, in like chronological backtracking SAT solvers and things like that, where the trail is a little bit different. And in that case, we might be able to use a more efficient system and make better use of the redundant edges we have. But yeah, thank you.
Thank you very much. Time for questions. David?
This may be a very naive question. So for
Yeah.
SAT solving, so what some people do is they do not try to optimize the proof that is produced by the SAT solver,
Right.
and then they use a tool that optimizes the output before trying to replay the proof in like in a proof assistant, where loading a large proof is really expensive. Have
Right.
you thought about post-processing?
That's an interesting question. So there is a quite a robust system for this in SMT on CVC5 at least, which is it's called like proof elaboration. So before you print out the proof, you do this elaboration section. I have not thought about using this for this tool. I'm not sure how we could be able to efficiently track like the redundant edges. So maybe we just compute them afterwards. I don't know. It's not a path that I explore, but it seems an interesting future work.
Hey, thanks for the great talk. I was wondering, I guess this might have been what you've kind of mentioned in the future works like, even though I wasn't exactly sure. So So previously you've mentioned that congruence edges, you kind of weigh how costly they are by kind of going back, and if you take this congruence edge, then you would also have to take these other paths to kind of associate a cost to them, because you know that, well, they cost more than what they depend on. I was wondering for the SAT stuff, if you just get A equals D, that also sounds like a dependency on the prior path, and if you use kind of the same idea of computing the cost of that the same way, then it sounds like it can't use that edge because it would be more costly.
So that is true. So that was one of the many approaches we tried for preventing the problem. So there are two ways of doing this. So you can either record how the term was derived in the SAT solver, and it kind of like what we called provenance when we were trying this, which is like which literals were dependent on by this literal. And in that case, it's going to be equivalent to the level system, because the weight is going to be monotonically increasing, because again, it's going to match exactly with the trail of the SAT solver. Another approach you can do is kind of analyze the literal afterwards and try to infer the provenance from that. And we tried that, and in theory it could work. So we didn't produce any proof which was invalid, but the proof are still rejected by the SAT solver, because the SAT solver expects that the specific trail it has, which is I guess like a topological ordering of the implication graph, it expects that that specific topological ordering is respected, which is one of the things that might change if you have a different architecture for the SAT solver. Does that make sense?
Yeah, I think let's chat afterwards.
Yes,
I think it might depend on more SMTs that I just don't know.
Yeah, cool.
Thanks.
Okay. Other questions? Okay, I do have a quick question for you. Can you go back to your slide? I think it was 32. Yeah. So the final, this is the reduction in the final proof size, right?
Yeah.
In the middle column. I assume this is the average over that 160,000 benchmarks. But what is the standard variation? Because in some of them you may gain a lot, in some of them you may not gain anything.
So
what I'm saying is average may actually not be a good representation.
Yeah.
You might be doing much better than this in the majority of them.
Yeah, that's a good question. So we did include the scatter plots similar to this one in the paper. I didn't include here because they're kind of boring, right? But the general idea is that it's very close to the diagonal. So there's not a lot of variation as there is in the runtime. It's mostly consistent.
I see. So the average is a good representation.
Yes, in this case it is.
Right, fair enough. Okay, any final questions? No. Okay, let's thank the speaker again.
Thank you.
Hello? Welcome to the session on Models 2. So we're going to have 3 talks. The first one is going to be presented by Noah. It's going to be on atomic gliders and cellular automata as language generators. Without further ado.
Thank you, Anthony, for the introduction. And yeah, hi, everybody. So my name is Noah, and today I will talk about our recent work, which is exactly atomic gliders and cellular automata as language generators. Some of us may be familiar with the concept of cellular automata, while some are not, but not to worry, we'll set the record clear. So we will start with some background and origin of the cellular automata model. Cellular automata were introduced almost a century ago by von Neumann and Ulam as a self-reproductive biologic system. It became popular thanks to the help of John Conway, who introduced Conway's game of life, which happened in the 1970s. One of the aspects that make it so appealing to other people is the fact that those kind of systems create the illusion as if something is living within the system. Those kind of object interaction within another assumed to be as a self-reproducing system, something that lives within this two-dimensional system. Next came Wolfram in the 1980s that considered the systems as a one-dimensional cellular automata in the simplest form, having only 2 states, black and white, and the radius of the system, which we will explain in more details in a bit, is only 1. Yet those seemingly very simple structure produce very unique abstraction and modification as an evolution over time. Meaning, whereas John Conway's had a 2-dimensional cellular automata that reproduce system that seems to be living, those kind of abstraction assume to have configuration that evolve over time, and this space-time diagram produces something that is pleasantly looking for a person, which make it more compelling. Over the decades, those kind of aspect and usage of cellular automata has spread across many domains. Most fundamental ones are biology as pattern recognition, epidemic spread, also in physics as lattice-based models and fluid dynamics, and even distributed systems, CA-like model are considered for parallel systems, self-organizing behavior, and many, many more. But what might be surprising for some of us is that despite this wide range of application over the decade, cellular automata are still typically considered to be some evolution of space-time diagrams, and not considered in a more formal aspect as we will usually consider them. So from a formal method perspective, we are usually considering what will be the language that the model can generate. How can we compare between different cellular automatas, and what we will do about the behavior that cellular automata impose. And indeed, mathematicians pursued this direction as well. Hedlund, along others, pursued this direction from a mathematical foundation basis and described the systems as language. However, they consider what term to be language acceptors. They ask the question, what would happen if we start from initial configuration, whether the system would stabilize or non-stabilize, some kind of an accepting condition. So while closer in spirit to what we want to do, it's still insufficient for our purpose, because we consider languages as generated by a cellular automata rather than being accepted. And from a formal verification perspective, we would like to consider the evolution from a set of initial configuration, what will be seen as the evolution grows. Meaning, we don't care whether specifically it would stabilize at the end, but we want to see what will be seen in the future. That way we can ask questions about safety, whether we will never see some unwanted behavior. We can ask a question about reachability, whether certain configuration would be reachable at the future, and so on and so on. So this is the roadmap that we have for this presentation. We will start with a very high-level description of the cellular automata. I want to create some kind of motivation and introduction to the model, and to allow you to have some kind of visual simulation of what to come. Next, we will use this definition to understand the gap that we try to cover, which we did by introducing the glider as a semantical unit. We will get to that, and conclude with our main contribution and the dynamic of the pattern and some conclusion for future works. So we consider an infinite line indexed by the indexed by the z numbers by all the indexed, meaning to infinity and to minus infinity. And each of those states is a process. Each process holds some kind of a value, could be seen as a state that it has. And usually can be considered as some color. As we saw with Wolfram, it was black and white. In here, let's assume it's pink and blue. So given this infinite line, let's consider some finite fragment and see what happens. So in this finite fragment, each of them is affected and evaluated based on the local interaction that it has, meaning every process has some kind of a neighborhood that determines what would happen in the next iteration as the configuration evolves over time. So if we consider only immediate neighbors, then it could be seen as a neighborhood of radius 1, and that will be the entire neighborhood. But in general, unlike classical elementary cellular automata, we consider systems that can have arbitrarily large radius, any natural number. And so it could be r equal to 2, r equal to 3. It all allows under our consideration. But to keep the example a bit simpler, we'll use r equal to 1. The evolution is defined by some lookup table. This lookup table determined in a deterministic manner what would happen, meaning if we have r equal to 1, meaning every neighborhood is of 3 cells, then the lookup table tells us, given a neighborhood, what will be the next state. So we note that, for example, this is the neighborhood of the middle cell, meaning those 3 current values will determine what will be that value in the next iteration. And we have a neighborhood that the neighborhood set is defined and fully deterministic, meaning although I show here only partial of them, you could assume that for any feasible neighborhood, any such set, there will be a value that dictates what will be the next step. So if we look on this evolution, the processes move one step at a time, and you can see that each of them looks on the neighborhood and look what will be the next steps. Now, although this presentation seems to be in a linear order, in essence, all of that happens simultaneously for all these infinitely many processes. So what would be is that a simulation would be something like that. That's one iteration. Given a configuration, the next one will be as follows. And so if we do that and consider infinite duration of by infinite configuration that evolve over time, what is being considered is actually the space-time diagram. It creates some kind of a visual representation of what to see. Now, shifting back to the classical cellular automata, such a transition would be something like that. Starting from an infinite configuration with only one black cell, then following some deterministic rule, apply something that is way more impressive than one might expect, given the deterministic and the entire variant. This is one of the rules that Wolfram introduced, creating the Sierpinski triangles, and we will see how everything is connected. So, before proceeding, let me fix our setting. What we consider is a one-dimensional cellular automata with a regular set of initial configuration, deterministic transition relation, and the natural question that comes to mind is that it looks very much similar to regular model checking. And so it leaves another question open. What exactly is being evaluated in this procedure? What exactly determine the behavior of such a system? So let's look on a classical example from regular model checking, the token passing protocol. In the token passing protocols, we have some finite yet fixed number of processes. Assumingly, classical variant is that the left most process has the token, and each iteration, the token is passed to its right until reaching the finite location, because we assume finite number of steps. So, crucially, this assumes the finiteness of the system. If we will try to implement the same thing for a cellular automata, then we lose what makes it regular model checking, because cellular automata are on by infinite configuration. Thus, this evaluation would never be actually done, because we could always continue more and more and more. So this already puts us outside of the frame that regular model checking imposes. Yet, to explore the intuition and the expressivity of such a model, we introduce a new type of protocol, what we term the two captains protocol. What we said is we have one red captain and one blue captain. At each round, each of the captains recruit a new player to their team. Let's assume that the red is spread to the right and the blue is spread to the left. So, turns are progressing and the rounds are progressing as well, and in each direction they maintain an equal number of red and blue. Now, although the pictures are very nice, we can also do that with the formal model that we have. As a cellular automata, we can consider that to be initial configuration with only one blue and one red cell. At each step, each of them recruit one new player to the associated direction. So, it is important to note that in this perspective, each row, each bi-infinite configuration, is the configuration under consideration. And unlike classical languages, when we say that a word will be the sequence of action we pursued, in this perspective, each configuration can be seen as sliced out and being a word in the language that we create. So, in a bit more details, what we do is kind of a projection. We keep only the active cells. Those that yet to be chosen could be assumed to be idols or something like that. But we look on the different ones, and each time step produce one word to the language. Looking on the overall observable configuration introduces a new language, which is the language of R to the power of n, B to the power of n, assuming red and blue for R and B. This already is a context-free language, which is not regular. Now, the key point is that these formal aspects created only by the local interaction that the system imposes. We started with one initial configuration. We impose only deterministic local rules, nothing that assumably create another power or memory to the model. Yet we exhibit something that is more than regular abstracts. So, if we view cellular automata language generators from this new perspective, what becomes the question is, how do we define the behavior that creates the semantic? How do we make sure that starting from the semantic unit and reach out to the language that we actually generate? What will be the unit that creates this kind of relation? This is where gliders comes into consideration. So first, that will be the sum up of the intuition. I know it's a bit high level. The paper is full with formal definition for all of you that might consider, but I wanted to make it clear and intuitive for you. It's what to come. So we turn now to the second part of the gliders. Very intuitively, very high level. I want to introduce some kind of vocabulary. How can we discuss this unit of semantics that create the languages over time? So we want to create something that represents it. Gliders as a term were already used in cellular automata literature. Usually what they mean is some kind of multi-cell variant that reappear in the system under some shifting periodically over time. But those kind of definition varies between paper to paper, and we wanted to make it much cleaner and more explicit to our requirement. So what we took is a glider, what we term an atomic glider, which is a single cell that moves across the grid in a constant manner. Let's see what it means. So we track atomic gliders. It's a one-cell carrier that moves across the grids, and we ask whether the local rules, those kind of transition relation that is deterministically defined, imposes some kind of a shifting across the board. So formally, this intuition is creating glider as a pair. Glider means to have some kind of a sigma, a value, or a state, could be the colors that we saw earlier, and it should have a velocity. Once again, it's important to note that unlike the elementary cellular automata of rule forms, our radius are not determined to be between -1 to +1, but for arbitrary large r. For example, in here, assuming that the radius could be large enough, then our local interaction, the formal rules, could imply that some kind of transition moves 2 steps to the right, 3 steps to the right, depending on our neighborhood. And so we create some kind of relation between them. Okay. Any questions so far? Okay. So, this perspective in gliders is not introduced in terms of, let me rephrase it. These gliders, in essence, allow us to create some kind of a semantical relation between 3 components of the system. What we have is set of gliders, set of initial configuration, and the language. So, given a set of initial configuration and a set of gliders, one can reconstruct what the generated language is by the cellular automata, because those gliders are defined by some kind of the local rule function. Respectively, assuming that the CA generated language is glider expressible, then we could do the other direction and to create a derivation of the set of gliders that, given a set of initial configuration, imposes the language in question. So there is kind of a relation that helps us to show what languages and what set of gliders allow for the expressivity results. Now, so far we talk about gliders in isolation, but in reality, when we want to talk about expressivity languages, we want to look on set of gliders that interact simultaneously. So let's consider this aspect. We start with initial configuration with 1 blue cell. Now assume that this value, the blue cell, has 2 gliders that are associated with it. One with velocity 0 and one with velocity +1. So, as every turn progresses, the gliders, in essence, spread across the board. Because even though some of them may be adjacent or even overlapping, they agree upon this decided state on the next step. Because if this cell wants to be blue and that cell wants to be blue, then although both of them would imply blue here, it's non-contradictory because they agree upon the next value. So now, if we add 2 more cells, we consider now also the red to be a value, and it also have 2 velocities of its own. The coordination between the 2 of them in reality create what we saw earlier as the 2 captains protocol. So we started with something that is well-defined, followed by the gliders, and it's very important to understand that no non-determinism occurred here. Everything is fully defined. Initial configuration in that part is only 1. We have only 4 gliders that follows precisely from the local rule interaction. Yet the observed behavior creates expressivity that might be surprising, since we came from the aspect of regular model checking, which preserve regularity and not context grammar. So, if we consider many gliders that evolve together at the execution, we might want to understand what will be the languages in question, what will be the expressivity result of such a system. So, given a set of initial configuration and gliders, we get a CA-generated language which could be quite expressive. How expressive? That's exactly the point that we want to explain. So, we started with regular initial configuration, deterministic local rule, and we already saw before that observed languages are not necessarily regular, as of the AN, BN. But those kind of aspects can be even more expressive, because although this is already shown, by very similar aspect of application of the gliders in connecting with one another, meaning without an isolation, but rather a set of such gliders, we can impose much more complex languages as such. This one, still starting with 1 initial configuration. That one has 1 red, 2 blues, and 1 purple. And a set of gliders. Now, this set of gliders create a language which is a to the power of n, b to the power of 2n, and cn. That one is already more than congruous free grammar. And this kind of relation still maintained, because what happens here is the blue preserve all occupied position by the 0, and the +1, -1 allow it to spread to its sides, creating 2 new occurrences at every iteration. For the additional one, because in a sense, it could be seen as if the blue pushed them aside, they need to be moved one cell to the side to maintain the number of occurrences, and additional one that allow them to create a new value. So in each step, both A's and C's create 1 new iteration, while the B's create 2 new iterations, maintaining this kind of AN, B to the power of 2n, C to the power of n.
Can you notice that one gives you, like, one spreads the blue and the other one spreads the purple?
Sorry, I didn't
No,
follow.
because like you have several gliders.
Mhm.
Can you not have 2 gliders that maybe collide or something?
Yeah, so that's a great question. I didn't discuss it in this presentation, but in reality for our paper, we introduced a partial order between the gliders, and then they impose something else. But in here, we show that even without the complex part, it's already observed something way stronger. But a great question. So very generally, what we consider in essence is a family of systems of wi to the power of ei in some n, which is wi's are non-empty words over some alphabet, and ei's are some non-negative linear expression, which allow us to create languages such as those that we saw before, but so many others as well. And those kind of expressivity is way even context-sensitive languages, still allowed by something that assumingly is finite, regular set of initial configuration, and a deterministic rule function. So if we want to summarize what actually determines the expressiveness of what to come. So we know it's not only the local interaction by itself. It's not only the initial configuration by itself, and it's not even the glider by themselves. It's a coordination of the 3 of them that allow us to determine the expressivity to come. So the objects are the atomic glider as semantic unit, because in essence, they create the alphabet of this language. The second one are the velocity and the partial order. As mentioned briefly earlier, we want to understand how far away each of them spread, what will be the relation between each of them as time proceeds. And those kind of relation imposes structure that can be very much complicated and induce some languages that don't behave the way that one might expect. And lastly is the initial configuration. So now we want to do some kind of a reality check, because there are also boundaries. We do able to describe many languages, many expressivity results, but if we want to define what can't be done with those gliders, then the first one is that there can't be no global synchronization, meaning each of them has local interaction. The knowledge is determined by the neighborhood. It can't be that 2 separate locations in some way create some kind of a lockstep and synchronize what they are doing, because the information is bounded to the area. The second thing is no unbounded choice or some kind of non-deterministic. Everything is deterministic. Everything is well-defined. Nothing creates something in between. So some models that create some kind of noise or non-determinism cannot be generated by such gliders. And the last thing is that there is no hidden memories. What we see, the configuration as is, the relation as the neighborhoods that imposes, that's what the model has. There is no hidden memories that can produce something else. There is no cache, there is no heap, there is no other information. And so those limitations, although limiting the system, are semantic limitations that come from the model under consideration. So let me summarize our main contribution. This is a very brief summary of our paper, but just to give you a bit of a feeling. So the first one is the semantic notion. We introduce what atomic gliders are. As we mentioned, gliders in the cellular automata community are widespread and unfortunately not much of a consistency between the ideas that it introduced. So we wanted to take the core idea of what do contain glider as appear in the literature and to create the semantical unit as simple as possible. But it's important that atomic, it's not because it's necessarily the simplest, but because the semantic by itself cannot be even more refined, as it's a single cell that moves across the cell, determined by the local rule function. Secondly, we provide a language theoretic result for cellular automata as language generators. Instead of reasoning directly on the space-time diagram that the cellular automata imposes, we study the languages that are being induced in the observable glider domain. And the third, within the framework, we introduced a new expressivity results. Because, as we mentioned earlier, some mathematicians did consider the model, but usually, in order to make it reasonable, they considered a finite lattice rather than by infinite configurations, which maintain the expressivity of the initial configuration under consideration. Meaning, if you only want to stabilize and stuff like that, then you cannot create more expressivity than the one that you introduced in the beginning. Yet, in our results, the fact that we have the initial configuration that are regular, the set of deterministic rules, which in essence can be seen as kind of a transducer that maintain the regularity, still allow us to express something that is way more expressive. As we saw, we contain context-free grammar, context-sensitive grammars, and even beyond. So, some outlook and future works. So, the first thing is the verification-oriented abstraction. As we said, gliders are semantical units. So, one may consider from the verification perspective, what will be the way to reason about them, to create something that distributed system can be reasoned about in an infinite distributed system across time and across infinite domain. And the natural question will be, first of all, decidability. Understanding which properties of such system with the glider semantics, with their unit, can be algorithmically checked. The second thing is learning. If we want to learn such a system, how can we infer the system? How can we learn the system? How can we do that without knowing a priori knowledge about the system in question? And finally, there is an abstraction refinement. Using glider as semantic building, this allows us to reason about the system that can be composed or refine the capture richer behavior, because as we saw, it's very much a building block. It's just one cell that moves across the cell, across the grid. The information is given by the local rule function. Yet, the structure within it, as mentioned earlier, has a partial order, has a refinement, has a reconstruction, and also the variation from a system could be even more refined and more abstracted to languages with more expressivity results. And by that, I will conclude my presentation. I'll be happy to answer any questions. Of course, you could also reach out later on, and I would like to use this stage to also mention my upcoming initiative. Together with Andoni Rodriguez, we introduced the workshop about post-AI formal methods to take place at POPL'26 this year. And we hope to get it around as to represent the formal methods in the AI world. So that's pretty much it, and thank you very much.
I think we have time only for one question. So anybody who has questions?
And of course, any other question, you are more than welcome to come by and we can chat.
Thanks for the great talk. It was super interesting. Did you also think about two-dimensional, like automata, how the languages look there? Does it make sense to ask that?
So it's somewhat of a question. I would say Because if we want to look at the visualization that comes across the time, if you do it in 2-dimensional, then in reality you create some kind of a cube of information that proceed. So although it has some kind of an interesting behavior, the initial idea came from the elementary cellular automata of Wolfram's that seemingly create something that is pleasantly and well behaved, yet very much complex. But I don't think that we actually checked much about the 2-dimensional. It's a very interesting question. So yeah, sorry I don't have an answer, but yeah, it's a great question.
Okay, so I guess you can set it up first maybe. Can I just maybe ask a super quick question?
Of course.
I think you can apply some techniques from regular model checking to analyze this, right?
Precisely, yeah. This is an idea that is already in progress as a future work.
Yeah, I mean, quite a natural thing considering Dana's background. So she did a bit of work on RMC. Okay, so thanks again. Yeah.
Thank you.
Right. So now we are ready for the second talk. It's going to be given by Luca. It's on reachability in multi-agent transfer systems. The floor is yours.
Yeah. Now it's better.
Okay, now it's much better.
So yeah, I will present you my work about reachability in multi-agent transfer systems, which was a joint work with Loïc Elouette, Nathalie Bertrand, and Angel Lefaucheux. A little bit of motivation first. So what you can find in our model will be some number of agents that have a resource on them that carry an energy level, and there will be some quantitative constraints on this energy. And the agents will try to perform to achieve some reachability objective. And what is new in our model is this notion of transfer. Our agents will be able to perform a transfer of this energy, and this is basically what you can find, all of this, in urban transport systems with regenerative braking. So for instance, you have a train that brakes. It converts a fraction of its kinetical energy into electrical energy, and then it sends this new energy to another train that is accelerating. Okay, so I will first present you the model, the proper model of transfer systems, and the different variants that we considered. And then I will focus on a single variant, try to convince you that our result of complexity for this variant is true, and then I will have a small part of conclusion. Okay, so first I want to, before to come to the transfer system model, I want to present it with a single agent variant first, which is way simpler because there is no transfer, there is only one agent. So what you can find here is a graph on which there is a single agent moving. There is an initial state where the agent initially is, and there is an objective vertex here, which the agent tries to reach. And so the agent has an energy level here, initially it's 0, and when the agent moves through an edge, it gains in energy the amount you can find on the edge. I remove the mouse. Up. But the energy level cannot go below 0, so you cannot go through this edge here, but you can go down and then reach your objective vertex. Okay, so this is for one agent. And now for multiple agents, so you will have the same thing as before, one graph for each agent, an initial state and an objective state, but what you will find that were not present before will be these green and red boxes, which are called transfer groups, that we call transfer groups. And when two agents are on states of the same transfer group, they can send any amount of energy from one to the other. Okay, and the other thing that we need to consider is how the agents move relatively from each other. And we considered 3 different semantics for the synchrony, so asynchronously, synchronous, and weak synchronous. And I will precise this a little bit later. So formally, what you find in our model is one graph for each agent and a set T of transfer groups, which is basically these red and green boxes here.
So you can transfer the +3 to the other guy?
Yeah, that's it. So here, suppose the agents move synchronously. They move one step. They are both in the green transfer group. This one has 3 energy units, this one has 0. Then one can send any amount, 1, 2, or 3, to the other. Okay. And our formal problem is a reachability problem. So we give a transfer system a set of initial vertices and a set of objective vertices. And the question is there a run from a starting configuration, so 0 energy units for each agent starting in each initial vertices, that reaches a configuration in which each agent is on its objective vertex. Okay. So the 3 different semantics that we considered, asynchronous, synchronous, and weakly synchronous, I will present them using these small examples that you can find here. So first, for the asynchronous semantics, in this semantics, the agents move one by one. So for the agent to reach their objective here, you can ask the first agent to move to P1, and then it has 1 energy unit. A2 is still on Q0. It can send the 1 energy unit to A2, and then A2 has 1 to pay for this edge here. And A1 can also reach its objective, and you have this run that represents what I just explained. In synchronous semantics, however, this configuration, starting configuration, is a deadlock because in synchronous semantics, the agents must move together. And here, agent 2 cannot move from Q0 to Q1 because it doesn't have the 1 energy unit needed. And finally, there is the weakly synchronous semantics, in which, once again, we require the agent to move together, except if the agents do not have any possible move to fire, any edge to fire. So for instance, this is the case for agent 2 here. There is no possible move for this agent. So A1 moves alone first. Then it can send, via this transfer transition, the 1 energy unit to the agent 2, and then they reach their objective state together. Okay. And so along the different semantics, we also consider different types of transfer modes. The first is transfer by groups that I already presented. This is a basic case. We have potentially several transfer groups. And the second transfer mode is global transfer, in which you have a single big transfer group, which covers every vertices of the system. And in this second mode of transfer, every transfer is always available among any pair of agents, any pair of vertices. So virtually, you can think of it as the agents share a big common energy level. Okay, and so this is the same example here and there, except that here we consider global transfer. And with this instance here, we have the interesting following fact. It's a negative instance for synchronous semantics and transfer by groups, but it's positive when you come to global transfer, and then it's always positive with asynchronous semantics. And this justifies that these problems, these different combinations of transfer modes and semantics are different problems, and so that's why we studied them separately. So maybe a little bit of explanation. With asynchronous semantics, why is this a positive instance? So here, what you can notice is agent 1, the first agent, has a positive loop here, but it has a starting cost of -1. So agent 1 needs to meet the agent 2 in the green transfer group. Agent 2 sends 1 energy unit to the agent 1, and then it can start to take his loop, accumulate as much energy as it wants, and then give this energy through the red transfer group here, and both agents are happy. This run that I just described is also possible with global transfer because it's just less restrictive. Okay, so this is positive and this is positive, but this with synchronous moves and transfer by group is negative. So here, agents must move together, but for agent 2 to pay the -100 here, they must agent 1 must have accumulated enough energy and then give it through the red transfer group. But to do that, they must spend as many move transitions between the green transfer group and the red transfer group. However, you can notice here that agent 2 has at most 3 energy units between the two groups, transfer groups, and so it has at most 3 move steps to wait between the two transfer groups. This is not enough for agent 1 to accumulate the 100. But in global transfer, when they reach the middle, their middle vertex here, you can notice that every 2 steps, there is globally 1 energy unit that is gained. So here, -1 + 4 is +3, and here -1 - 1 is -2, so globally +1. The whole system enters the 2 steps loops that accumulates energy, and then everybody can be happy ultimately. Okay. So here are condensed version of the different results we came up with in the paper. This is all the complexity results that we found combining different semantics and transfer modes. And that you can see is it's pretty interesting that it ranges from NP-hard to undecidable. However, there are some complexity gaps here and here that we hope to close one day. And so the variant that I will focus on is transfer by groups and asynchronous semantics. So here, transfer by groups, you have the local boxes, not a big one, and move asynchronously. Agents move one by one. Something that I want to emphasize on this small instance here that will be helpful just right after is that in this example that you can notice that what you can view, what you can imagine is that agent 1 helps agent 2 to reach its objective. And this notion of helping will be useful to prove the p-space membership of this instance, of this variant of the problem. Okay, so to prove p-space completeness, we first prove p-space membership and then hardness. How did we prove p-space membership? So we obtained an exponential bound of the energy levels of the agents. This means that the energy level never needs to go above this exponential bound. Where does this bound come from? So suppose that agent 1 has enough energy to do anything that it may have to do. And by may have to do, I think of helping every other agent of the system. So here, helping is a more generalized notion that I presented previously, because it might be helping indirectly via another agent or many other agents. So here, agent 1 sends some energy, has to send some energy to agent 2, and then agent 2 in turn helps agent 5 and agent 6. So agent 1 needs to provide for agent 2 to help agent 5 and agent 6, and then reach its own objective. And the thing is, if you have enough energy to do anything, these red arrows here, it means reaching, trying to meet the other agent in a transfer group, and the green arrow reaching your own objective state. So accomplishing these arrows, if you have enough energy, you can say, okay, I don't care for the negative cost, and I move straight to the point, just as a simple path. And so here what you have is that if you have enough energy level, every arrows you can find on this graphic can be done using a simple path on the graph. And this is helpful to bound the energy that this simple path costs, and so that the energy that agent 1 needs to provide to help every other agent of the system. So we take B to be the highest cost of a simple path of the whole system. And this is, so because we encode the weights in binary, this bound B is exponential on the biggest weight, and so exponential in the transfer system. Okay, so now the question is, how many arrows are there on the system? How many times do I have to pay the B at most? And obviously there is one green arrow for each agent, because each agent needs to reach its objective. And there is one red arrow for each agent except the first agent, agent 1. So this is n plus n minus 1 to n minus 1 if you have n agents times B. And this is an exponential bound. So now you know that you can store configuration in sorry. You know that to store a configuration you need at most exponential weights. So in binary, at most polynomial space to store these weights. And so you have a non-deterministic p-space algorithm, and with Savage theorem you have a p-space algorithm that solves this problem. Okay, so this was membership. And now, what about hardness? So to prove that this problem is p-space hard, we reduced the reachability in safe Petri nets to our reachability problem with asynchronous semantics and transfer by groups. What is safe Petri nets? So it's the same thing as Petri nets, but you can never have more than one token in each place. Okay, so this reachability problem is known to be p-space complete, and this is why we reduced it to. So this is why we have the p-space hardness. The first thing that I want to make you notice here is that in our reduction there is one agent for each places of the Petri net. So here I have place 1, 2, and 3. There is just a very small safe Petri net. I have 3 agents, 3 places, and so 3 agents. And I have some states that we'll call stable states for each agent. One that is labeled by 0 and one that is labeled by 1 that represents the amount of token there is in the corresponding place. So here, to encode the marking M, you have agent 1 on the stable state 1, agent 2 on the stable state 0, and agent 3 on the stable state 1. And now, the second thing we need to have in our reduction is a way to simulate the firing of a transition in the safe Petri net. And to do that, we added a new agent that we call the controller, and that will, between each stable configuration, choose a transition to fire. And when the controller chooses the transition to fire, it will take a path, and there are corresponding transfer groups that are linked to that path and to that transition. So here, if the agents want to follow the agent need to follow the choices of the controller because it's the only one that can provide for the 1 energy unit that it has to pay, etc. And so there are a little bit more details than that to accomplish the proof. Mainly, why do we need the 2 phases? But I will not enter in these details right now. The idea is that the controller chooses the transition, and all the agents need to follow the choice of the controller. And everything goes according to plan. We have simulated the right transition, for instance, here. So agent 1 goes from the state 1 to the state 0. Yeah. Agent 2 from the state 0 to the state 1, and agent 3 from the state 1 to the state 1. And you can enforce the system like that to follow the constraints of the transition. And so we obtain p-space hardness and p-space completeness of this variant of the problem. And what about the remaining boxes of this table? So the first thing to complete the filling of this table that we can notice is that there are some simple reductions that we can make among the different variants of this problem. So the first is between, so you can reduce global transfer to transfer by groups, because global transfer is just transfer by groups with a single transfer group. You can reduce asynchronous semantics to synchronous semantics, because when you add +0 loops on the vertices, you can simulate the weighting of the agent and the asynchronous moves. So you may always have one agent moving while the other wait. And you can reduce synchronous semantics to weakly synchronous semantics, because remember, so weakly synchronous semantics is the same as synchronous, except that you allow the agent to wait if they have no possible move to play. But here we add from each vertex an edge that goes to a bad state that leads to nothing. That costs 0, so it is always available, and the agents may never wait because they always have at least one move available that they must take, if possible. So it is not allowed in this reduction for the agent to reach the objective to wait on the states, so it means to reach the bad state. And with these 3 little, so here with only 2 little, with this result and this result, we can obtain that this variant is in p-space and that this variant is p-space hard. Then to obtain the NP hardness of this variant, so global transfer and asynchronous semantics, we obtain a reduction from subset sum. And to show that this is in X space, we reduced the reachability of this variant to VAS cover. Here, so we have p-space completeness of these 2 variants of the problem. We only needed to show that this one is in p-space and this one is p-space hard, because with this reduction, the third result I presented earlier, we obtain the completeness of the whole box, the two boxes. And we, once again, use the polynomial bound on the energy level trick to obtain the membership and reachability from, and we reduce, and there is a reduction from safe Petri-nets reachability. Okay, and then more surprisingly, so the undecidable box, we obtained a reduction from the Minsky machine termination problem to weakly synchronous and transfer by groups. Okay, and as a conclusion, so we propose a new model to represent multi-agent system in which agents may perform some form of transfer. We obtain a wide variety of decidability/complexity results with different semantics and transfer modes. And these results range from NP-hard to undecidable. Okay. And so for future works, the first thing that we want to do is close the complexity gaps that are still in the table. Ongoing works here, we raise the question of what if all agents are playing on a copy of the same graph. So here it's a parameterized question. And finally, also an ongoing work, what happens when we lose collaborative agents and consider that they play against each other. So it's about finding good Nash equilibria or subgame perfect equilibria. Thank you.
So thanks again, Luca, for the talk. I think we have a few minutes. 2 minutes more precisely, 3 minutes. Are there any questions? No? I have one, at least one question to start, just maybe to get the thing started. I was wondering why you can't just, I mean, maybe can you give the intuition why you cannot just convert the last case, the undecidable that you mentioned, undecidable to just Petri-net reachability? What's the problem with that? Why you can't encode the zero test?
The thing is, with weakly synchronous semantics, there is something that can happen that you cannot. Oh, you went too far. Sorry. Yeah, there is something that may happen that cannot happen anywhere else. Is that you can punish the agents for having too much energy, because then you can force them to move through an edge.
Okay. Yes,
okay.
Yes.
However, sometimes they maybe prefer to wait. So suppose here there is a -1 that leads to a bad state and a -2 that leads to good ending. The agent prefers to wait for another agent to send him energy than having one energy and going to the bad state.
So because you can wait for a really long time, I guess, in this case?
Yeah, maybe. And so the zero test comes from here. You can test if the energy has at least one energy unit or not.
Right. Okay. How do you connect this to the problem that you mentioned at the beginning? Because here you have some kind of reachability. Well, I guess you want to make sure that it's a specific. I mean, if you look at the original problem that you mentioned, like the collision stuff, it's more like
here.
Yeah. So is this also like control state reachability, or is actually maybe reaching something with specific energy, something bigger than
so here a question that you may ask yourself is if I have an infinite run, what would be the best ratio of energy that I can transfer by move transition? we didn't elaborate about around ratio questions in our transfer system model, but it could be interesting. However, it may be more relevant if we had continuous numbers, so timed automata, I don't know. But you can consider, okay, my network, my transport network must accomplish a daily routine of each train moves along this whole trip and then reaches the end station. So this can be seen as reachability if you consider only finite trains. But then the question again is, what is the best amount of energy can I transfer along these runs? However, these are threshold questions, maybe. They are linked to threshold questions, and which are the.
Then you get essentially the problem that you're considering.
That's it.
Yeah, got it. Right. I think we kind of ran out of time. So yeah, thank you, Luca, again for the talk. So I'm not sure who's giving the last talk. You're giving the last talk. Okay. Yeah, because you were not here. I was checking. Can you maybe set it up first? Just to make sure that you are Ray, right?
Yes.
Okay. Okay. So we have the very last talk of the session. It's going to be given by Rui. It's about hybrid meta-learning framework for adaptive safe controller synthesis of dynamic systems.
Okay.
The floor is yours.
Thanks for your introduction, and good evening, ladies and gentlemen. And today I will present my work titled Hybrid Meta-Learning Framework for Adaptive Safe Controller Synthesis of Dynamical Systems. And this is a joint work with my collaborators from Zhejiang Scientific University. Okay, let's begin. Okay, let's show you the background. Cyber physical systems are increasingly deployed in safety-critical applications, such as the self-driving cars, air traffic control system, and the train control systems. And in these scenarios, failures can lead to severe consequences. As a result, controllers for such systems are required not only to achieve performance objectives, but also to provide strong safety guarantees. Formal safety verification offers a principled way to ensure that a system can avoid unsafe states. However, it faces some challenges, especially when the system becomes more complex and more high dimensionality. And this challenge motivates the need for adaptive and efficient safety controller synthesis methods, which is the focus of this work. So let me briefly review the existing approaches. Firstly, I will introduce the learning-based safe controller synthesis. And in this kind of approaches, the neural controllers are learned together with barrier certificates, often combined with counter example guided synthesis. And an example is a fossil. So, but this method provides strong safety guarantees, but they typically require solving each new system from scratch, which makes them inefficient when system dynamics vary. So meta-learning is introduced in this kind of problem. And the first kind of the meta-learning is called gradient-based meta-learning. And an example is MEML. So this kind of method enable fast adaptation and through shared initializations. Well, this method have been applied to control and stability certification, a single initialization is often insufficient for safety controller synthesis across systems with different dynamics and safety constraints. And in the last, I will introduce the model-based meta-learning. And this is kind of meta-learning to learn task embeddings to capture task structure and enables efficient task representation. However, this method is not usually designed for formal safety guarantees. And overall, all of these three kind of approaches cannot simultaneously achieve fast adaptation, task-specific synthesis, and formal safety guarantees. And this gap motivates the hybrid meta-learning framework. And based on above, we make the following key observation. Safety controller synthesis tasks are not independent at all. Although system dynamics and safety constraints vary, they share latent structure that can be learned and reused across tasks. And gradient-based meta-learning enables fast adaptation, but it treats tasks in a task-agnostic manner and relies on a single initialization. On the other hand, model-based meta-learning can capture task-specific structure through embeddings, but it's typically not designed for safety guarantees. So this leads to our motivation. We want to learn task structure for fast adaptation while enforcing formal safety guarantees. And this figure illustrates how we combine the model-based and gradient-based meta-learning. And in the left part, it is corresponding to the model-based meta-learner, which learns the task embeddings from the trajectory data, and these embeddings capture latent structure shared across the safety controller synthesis tasks. And the right part is the gradient-based meta-learner, and where the controller network and the barrier networks are adapted, conditioned on the task embedding learned before. And let's see the training and the adaptation process. The black arrows indicates the training process, and in the meta training is on multiple tasks, where both the embedding network and the controller network and the barrier network, their parameters are optimized. And the red arrows indicates the adaptation for a new system. We just use the limited data and enables fast adaptation to a new system. And then we follow it is followed by a formal verification to ensure safety. And now we considered a controlled continuous dynamical system with a vector field F and this. And the system evolves according to these equations. And the U is the control input, which is given by the feedback controller. And the system is defined over domain XD, and initial set XI, and unsafe set XU. And the problem or our objective is to synthesize a controller such that all trajectories of the system that start from the initial region, it cannot enter the unsafe region. And we guarantee the safety. To guarantee the safety, we adopt the barrier certificate or the control barrier certificate. And a barrier certificate is a real valued function. And as you can see, the barrier function separates the initial set from the unsafe set. And it enforces forward invariance through a Lie derivative condition, specifically in the right of this slide. The barrier function is non-positive over the initial set, and it is strictly positive over the unsafe set. And its Lie derivative is strictly negative over the 0 level set. And the control barrier certificate provide a sufficient condition for safety, which we use throughout our framework. And then it goes to our method. In the top of the slide, it is the model-based meta-learner. And in this one, the key idea is to represent each safety controller synthesis task using an embedding learned from the trajectory data. For each system or for each task, we generate the trajectory sequences consisting of the X, which means the system states, and the U, which means the control input, and the R means the reward signal that reflect the distance to the unsafe area. And then the sequences are processed by an LSTM network, and the final hidden state of the LSTM is the task embedding we use. And this embedding captures the task-specific information about the system dynamics and the safety constraints. And importantly, this embedding is not used to directly predict the control action. Instead, it conditions the synthesis of both the barrier and the control network in the next stage. And although each task has its own embedding, the embedding network is just like the LSTM network itself. It is shared and meta-trained across all the tasks. So let's go to the gradient-based meta-learner. Yes, it's done. After given the task embedding, we synthesize both the barrier and the controller network using gradient-based meta-learning. And the embedding is concatenated with the system state X, and they are used as the input to both networks. And in the inner loop, the two networks parameters are adapted to a specific synthesis task by minimizing a task-specific loss that encodes the barrier certificate condition that we mentioned above. And during the outer loop, the meta parameters are optimized across tasks so that only few gradient steps are required to adapt to a fast adaptation. And in this way, the gradient-based meta-learning enable efficient synthesis of task-specific barrier certificates and the controllers conditioned on the learned task embedding. So this is the new task adaptation phase. When given a new system, we first collect a small amount of the data and use those data. We generate the sequences and extract a task embedding using the learned embedding network. And then starting from the meta-learned parameters, we then perform a few gradient steps to adapt both the barrier certificate network and the controller network. And importantly, this kind of process does not require training from scratch, not like the learning-based approach. And it demonstrates that the meta-learned initialization and task embedding reduce the number of gradient steps for adaptation for new system. And finally, we ensure formal safety guarantees through verification. Learning alone is not sufficient for the safety critical systems. And barrier certificates provide a sufficient condition for safety, but we still need to verify whether a learned candidate actually satisfied the condition over the state space. And given after the synthesis of the controller network and the barrier certificate And after the synthesis of the control and the barrier certificate network, we encode the barrier condition into the SMT constraints, and we use the real solver to verify them. And if the solver find counterexamples, you will sample the If the solver find counterexamples, then they will be used to generate additional training samples, and the barrier network and the controller network will be refined accordingly. And this kind of process will be repeated until in a counterexample guided manner until all the conditions are formally verified. And safety in our framework is not based on empirical testing or simulation, but it is guaranteed through formal verification. And this is the experimental evaluation. We evaluate our proposed framework on a set of benchmark systems, including 2, 3, and 4-dimensional systems. And we compared our method against the fossil tool and the MML-based method. And the table reports the success rate and the computation time for each method. As we can see, our method achieve a higher success rate and while requiring less computation time. And these results demonstrate that the proposed hybrid meta-learning framework improves both efficiency and the reliability in adaptive safe controller synthesis. So to conclude, we propose a hybrid meta-learning framework for adaptive safe controller synthesis. And by combining model-based and gradient-based meta-learning, our method enables fast adaptation to new systems while capturing shared structure across the tasks. And the safety in our framework is formally guaranteed through SMT-based verification. And overall, this work demonstrates that meta-learning and formal verification can be effectively integrated to address adaptive safety synthesis problems. Okay, that's all. Thank you.
Yeah, so I think we have, it was a bit short in the sense that we have like, I think about 10 minutes or so if anybody want to follow up with questions. Yeah.
No. Hello. In the evaluation slide, what was the round? What does that represent? The round quantity.
This?
Yeah.
Round means the verification run by Derill. The Derill. We use Derill, and round means that after training we use Derill to verify, and if we find the counterexamples, we will do the training and verifying, and that's
okay. So the number of times you have to do this loop.
What?
The number of times you have to do this?
Time?
Yeah, the number of times you have to go back and forth between the training and the verifying.
I'm sorry.
So maybe like the I don't know if like you mean like the number.
I mean, if I understood right, you have to have the interactions you have to do with.
Yeah. So is it like the number of is the number of interactions like the number of counterexamples maybe from SMT?
I still don't get what you mean.
I mean, yeah. So we just want to know what round means. So
round means just as I said, after we trained, we get the two networks. We use the Derill to verify, and then if the round one means there is no counterexamples during the verify, we just get the red candidates.
That would be 0.
That will be 1.
1. Okay.
Yes.
Okay. So I think that's it. But what is this then?
This is like the ML-based approach cannot cannot converge. Yes.
Okay. I see. All right. Okay, so it's only not so many. It's all very small, right? All of these numbers.
Yes.
Only like one.
Yes, because the FOSL 2 is a state-of-the-art learning-based approach to the control, to synthesis control.
So most of the time is spent on the solvers or on the
training and
mostly on the
the time
training.
is including the training time and the verify time.
Yeah, but how much time spent by the SMT solvers?
Maybe just a
little bit.
A little bit, yes. Okay. Most time, in our method, most time is the training, yes. And but for FOSL, maybe some the verify time and the training time maybe a half.
Okay.
Thank you. So I have maybe two questions. So the first one is: so you said you use DReal, so there is some it's not precise, right? So does it occur the imprecision somewhere? Is it a bottleneck?
What DReal?
DReal is not precise, right? It is not exact. It's using some approximation.
No, I just use DReal.
Okay, so you don't. Okay, so you use DReal, but is there any problem with its imprecision in your approach? Is there a problem that DReal is not precise in what you're doing, or do you need to somehow handle the imprecision, or?
Is that approximation or?
Approximation.
Yeah, I don't know. Is it?
So DReal, it's not precise. It has some epsilons, right?
I don't know. DReal is not precise.
Okay, so maybe another question. So you're talking about synthesis, but there is another approach. Is like, so you're synthesizing safe controllers, right? And another approach is like to use an unsafe controller, but using some kind of shielding. Have you compared with these approaches?
No, I just compared to this kind of two approaches to synthesize the safe controller.
Okay, thanks.
So shielding is like instrumentation?
You're checking what's happening and detecting the unsafe behavior.
Okay, when it's unsafe, then you just like, okay, then you protect it. Okay. All right, okay. I have a very general question because I was a little bit confused because I don't know, maybe I didn't really understand at the beginning.
Yes.
What do you mean when you say, what is really the difference between model-based and gradient-based? What is model-based here?
Okay. Here?
Yeah.
Gradient-based meta-learning is a...
Well, I know gradient-based,
yes.
but what is model-based?
It's kind of, it's also called black box meta-learning. And you have a set of tasks, and the model-based meta-learning will extract embedding from the task and use the embedding to predict the network.
Okay.
Yes, that's the model-based meta-learning. It is not optimized. It is not optimization based. It is based on the model, the network to generate the task embedding and use the task embedding to do what you want to do. And that's the model-based meta-learning.
And usually and gradient-based is basically just using some neural network, something like that, or some kind of local search, or that's what it means here.
Actually, I didn't know that so much. I just know the model-based meta-learning is not really used in the safety guarantees, this kind of area.
More questions? I guess if you don't have questions, we are off for an early coffee break. All right, thank you so much again.
Okay, thank you.
4 o'clock.
Okay. Ah.
Yeah, just fine.
Hello everyone. So welcome to the last sessions of VMCAI. So I mean, it's a sessions about verifications of quantum program and the probability programs. Yeah. So let's welcome the first speakers. The first speaker is Yang Chao.
Yeah.
Yeah. He's talking about efficiently verifying quantum programs with few tickets.
Hello, everybody. My name is Young Chan, and this talk is titled Efficiently Verifying Quantum Programs with Few T-Gates, and it's a joint work with my advisor, Robert Rand. The short flow of the talk will be after an intro, we talk about the logic, and then automation, and then after a short case study, we talk about the enhanced version of the automation, and then a simple application on the quantum error correction, encoder correctness, and then limitation, future work, and conclusion. So why formal verification in quantum computing? Measurement collapses superposition, which is a special feature in quantum computing. So we cannot use classical debugging techniques such as breakpoints or printing out the value. And second, outputs are non-deterministic probability distributions, which means that empirical testing requires massive statistical sampling, which is expensive. And third, it's hard to distinguish from noise from errors. So static verification is the only reliable guarantee before execution. The problem is that state space explodes exponentially. An n-qubit quantum state is a 2 to the n dimensional vector over the quantum complex numbers. So the dimension explodes exponentially as the number of qubits grow. So state level simulation is infeasible in practice. So instead, we reason about logical assertions on the inputs and outputs. We introduced Clifford and T-gates. Clifford gates consist of H, S, and C0 gates. And the Gottesman-Ill theorem tells us that with only these Clifford gate circuits, we do not gain any quantum advantage because they are, the programs become classically simulatable on polynomial time. So we add a T-gate here, and we get a universal gate set. Universal in the sense that any unitary transformation can get approximated to arbitrary precision using these Clifford and T-gates. If we define T-count as the number of T-gates in a circuit, then the T-count matters for compilers because T-gates require high resources such as ancilla qubits or time. So compilers mostly try to prioritize minimizing T-count. So we focus on verifying low T-count circuits to ensure that optimization preserves the semantics. Our goal is an automated horse-style verification with targeting low T Clifford T circuits, where with the structure where we have structure-guided automation that produces checkable proofs in ROC. We introduce Pauli and Clifford group shortly. The Pauli matrix consists of X, Y, and Z. And the Pauli group is an n-fold tensor of the Pauli matrices with coefficients plus minus 1 and plus minus I. The Clifford group is the key, consists of unitaries generated by the Clifford gates, the H Hadamard phase 8S and the C0 gate. But it is also it can be also equivalently defined as the normalizer of the poly group, which means that the conjugation of the elements in the Clifford group maps polys to polys. So this means that we only need to update the poly strings to compute conjugation by Clifford gates or Clifford circuits in general. We implement a Heisenberg-style Hoare triple, where the poly strings are the predicates or assertions, and we take +1 eigenvector semantics, which means that the state satisfies the predicate if and only if the state is a +1 eigenvector of the predicate. And then the Hoare triple is valid if the postcondition becomes the conjugation of the precondition, where the conjugation is on the matrix semantics of the circuit. And then the soundness becomes the state is a +1 eigenvector of the precondition, then the evolved state becomes the +1 eigenvector of the postcondition. So instead of the typical backward reasoning of Hoare logic, we use forward reasoning along this conjugation. And we note that for Clifford gates, because they are normalizers on the poly group, the predicates remain as polystrings for Clifford gates, but this is different. This becomes different for T gates, which can produce linear combinations. As we can see in the conjugation identity, x gets sent to 1/2 x plus y. So the corresponding Hoare triple becomes, if we have a precondition x, then the postcondition of the T gate becomes x plus y, 1/2. And this can lead to an expression blow up with, for example, in the most bottom equation, if we apply T gates twice, then we get x plus y minus x without any term merging. So without term merging, this gets exponentially large, which will come back later. Intersection, to say something about the common +1 eigenvectors of multiple predicates, we have intersection predicates to express them. So intersection predicates represent the joint +1 eigenspace. And if we look at the circuit in the middle, this is an Bell state preparation circuit, and the above is the Hoare Heisenberg logic style computation, and the below is the state vector evolution computation. And the bold, if you look at the precondition of the Hoare Heisenberg logic style calculation, it's Z tensor I intersection I tensor Z for the precondition. And the corresponding state is 0 tensor 0, which is a joint +1 eigenvector of the intersection. And after the circuit, we get x tensor x intersection z tensor z, and whose joint +1 eigenvector is the Bell pair. The Bell pair is entangled, so it would be nice if we can be able to say about things which are not entangled, if we can tell whether they are entangled or not just by the predicates. And we can do that by separability predicates. This is just separability for a single qubit. The above is the Hoare triple, this is the circuit diagram we're going to use, and this is the Hoare Heisenberg logic style reasoning. The precondition and postcondition is both I tensor z, and the +1 eigenvector of I tensor z all looks like a state tensored by the 0 vector. The state where the state can be anything. This is corresponding to the calculation below, where you can just look at the starting point and the end point. The starting point, it starts at the any state tensored by 0, and then it ends by a different state tensored by 0. So just by looking at the Hoare triples, the predicates in the Hoare triples, we can guarantee that the second qubit can be separable from the system, and it is 0 as the +1 eigenvector. This separability can be generated to non-additive multiqubits. They have to be non-additive because additive predicates, it's hard to tell commutativity and anti-commutativity for additive predicates. So we only focus on non-additive for multiqubits. And in the tool we have syntactic well-formedness, which denotes Hermitian unitary trace 0 matrices, which are dimension correct. So instead of checking matrices, we check the syntax instead. And because of this, side conditions reduce to syntactic checks, which can be discharged automatically. And by automation, we use rule chaining. Rule chaining is a deterministic forward reasoning along the circuit. We're deterministic in the sense that there is no heuristic-like proof search behavior. The input is P circuit Q, or the Q can be just a blank, or can be unknown. Then the proof becomes a propagation of the predicate gate by gate. It starts from P and propagates through the gates and ends on the given Q or the blank. And the output is a proof with the discharged side conditions. The proofs are justified by the Hoare-Heisenberg rules, where the rules are all Roch checkable with no external solvers involved. We have two main tactics, where the first is validate. It's a propagation of predicates, assuming that we already have a postcondition given. It fills in the intermediate steps and checks the final Hoare triple. We can use it. It's a minimal interaction for the users. And for the case where the postcondition is unknown, we have the solve placeholder tactic. It fills in the intermediate predicates and produces the postcondition, and it places the filled-in triple in the Roch context, so we can observe how it looks like before finishing the proof. And the Hoare triple looks like there exists Q, preconditioned circuit Q, and then we do solve placeholder, and then we can observe what Q looks like before doing assumption to end the proof. An example is the Toffoli gate, which is a controlled NOT gate. It is the reversible AND gate in quantum computing, which makes it essential but expensive. We use the decomposition on the right here, which involves multiple T gates. And those T gates can make things very messy. This is the case when the precondition is I tensor Z. And if we go through the Toffoli gates, we get the messy postcondition expression here. This can be done by, if you know the postcondition, you can type it in and do validate, but if you don't need to bother because solve placeholder does the inference for you and you can just observe what it looks like. And we test the additive predicates by repeating T's on a single precondition X, which should return just X after 8 T's because it's periodic. But the problem is that automation does not merge additive terms, so we expect something to go wrong, which is the case on the graph on the left, which is the runtime versus the number of T gates on the previous example. You can see that it bottlenecks as the T gate grows, And we failed to verify that 8 T's is I because the system hanged after 7 gates. This is very inefficient considering the periodicity of the T gates. So this gets resolved later on, but if we look at the bottlenecks first, the bottleneck is rule chaining and expression growth largely, where the rule chaining is works on the tactic level. So it's a bunch of applies on the inference rules, and it gives a bunch of syntactic side conditions to check. So per step, symbolic cost dominates the runtime. And expression growth, as we just saw, the term is not merged, so it blows up exponentially. And so that motivated an enhanced automation where we solved the two bottlenecks. The first part is direct post-condition computation of the direct computation of the post-condition in Galena. So we have a compute PC function where the function is a recursive function whose correctness is pre-verified. So instead of using LTAC on the inference rules multiple times, we can just use the fact that the compute PC function is pre-verified and then just let the compute PC function compute the whole thing, which is very fast compared to repeated tactics. And the second part is reflexive normalization, where we merge like poly terms with scalar reduction. So if you look at the automation versus enhanced, the automation does not merge terms, so we, after T gates, we get what we saw, x plus y minus x, where the x can get canceled out and y can get merged, but they don't. And the enhanced automation does this and just returns y. So this enhanced automation solves the blow up in the example we just saw. This is the same core logic but stronger automation. The impact of enhanced automation is an approximately 1,000 speed up overall in our machine from seconds to milliseconds. And as we saw, it prevents the blow up in the test for that one contrived example, which is kind of better because instead of being a function, naive function on the number of T gates, it's a function on the T gates which do not merge, so it's a little bit better in that regard. And the proofs stay minimal. It's just validate REFL, and the side conditions remain syntactic. We apply this on quantum error correction, which is a way to protect information on physical noise. The encoders encode a single qubit to n qubits, and the code space is a subspace of the qubit space, which is a subspace of protected valid states, which can be expressed as an intersection of stabilizers, which are polystrings. The stabilizers act as quantum parity checks, where the -1 eigenvalue is signals an error, and the +1 eigenvalue either signals a quiet error or no error at all. And we check encoder correctness, which is that we ensure the circuit maps the input into the valid code space for Steen and Shor encoders, where the Steen maps 1 qubit to 7 and Shor maps 1 qubit to 9. We check that the input x goes to logical x and the input z goes to logical z. the Hoare triples, 2 Hoare triples on the bottom are for the Steen encoders, where we can see that the above, the x1 goes to the x bar, which is the logical x, and the z1 goes to z bar, which is the logical z. And the G1 intersection G6 becomes the code space. So this is checking 2 things at once. The first is that the input does get into the code space, and second, x does go to logical x, and z does go to logical z. The limitations is that T-gates that are spread across many qubits still blow up. This is the same for the enhanced automation case as well, because it's the structure of the logic itself looks like that. So there's no going around. And for future work, we want to support measurement with faster symbolic term structures. And we want to support quantum error correction beyond the encoders, which require measurement and conditional branching with classical variables. So the conclusion is that we mechanized and Hoare-Heisenberg logic in ROC for low T-Clifford T-circuits. We have syntactic predicates, which enables deterministic forward reasoning, and ROC checkable proofs without external solvers. And for scalability, we have it is efficient for circuits with limited T-gates, but it blows up for many T-gates across many qubits. The enhanced automation was developed after the VMCAI artifact, so it's not in the paper, but it's on GitHub. It's in Inquire/Heisenberg logic at reflexive automation branch. And we give thanks to William Spencer for making reflexive automation happening. That is all for the talk. Thank you very much.
So questions?
Thanks, Yong-Sung, for a nice talk. So I want to ask, like, your work is actually trying to address the case where you have a few T-gate.
Yes.
But in your example, you use encoder as example, which has no T-gate.
Oh yes, that is
and
true.
that is actually sufficient to use just some stabilized simulation to handle. Have you tried any case with like interesting case with a few T-gate?
Few T-gates example. Quantum error correction is not that one. We mostly did as a stress test, we mostly did test how the additive predicates split each other, but I don't think we did an actual close to real world test on the T-gate, low T-gate style circuits.
So it's a future work, right?
Yes. Oh yes, except for Toffoli, but that's just one of the example.
Thank you.
Thank you.
More questions?
Thanks for the talk. I was wondering, so like in practice, like for a quantum algorithm that's offering quantum advantage, the T-gates must be distributed throughout a quantum circuit in such a way that like the conjugation action of the overall unitary on any poly must have a lot of non-zero coefficients when expanded in the Pauli basis.
Yes.
Like, so there must not be very much of this of this simplification that can be done. So and I which you acknowledged, like, in saying, but so I guess my question is kind of like yeah, I guess about the scalability and what role this would have when looking at like the size of kind of quantum programs or something that would be offering real quantum advantage.
So the first thing is that in future work we are firstly tackling the support for quantum error correction, which is stabilizer based without T-gates. So we are trying to support measurement first and with classical variables, but with multiple T-gates, examples with multiple T-gates, I will suspect that it will with more T-gates it will eventually blow up, similarly to what we just saw in the graph. Not as that bad because the enhanced automation kind of made the runtime more faster, but it will still algorithmically, I am expecting it to blow up similarly.
So, like, for instance, like, have you tried it on like the quantum Fourier transform or something like that? I would think it might blow up pretty quick.
We didn't try on the QFT yet, but that would also be as a future work.
Thanks.
Further questions? We still have time. So I have a quick one. So I mean, my first impression about is Heisenberg Hall logic. You can express the separabilities
yes.
property. Yes, but yeah, have you tried to verify some separability of some algorithms, some implementation of algorithms, or?
What was it? Sorry, I forgot the circuit, but there was an example circuit where we checked the single qubit separability. So for ancillas where we undo the computation, we can get separability for that uncomputed ancillas. It does go through, but the problem of multi-qubit separability is that the T-gates make them additive, which doesn't behave well. So just for single qubit, the uncomputed ancillas do work as an example, but we can't specify we can't specify the stabilizer states in the Gottesman tabular way, tabular style, because the T kind of blows the terms up.
Okay, thank you.
Okay.
So, no further questions. Let's thank the speaker again. So, yeah, our next speaker is Marco Lewis. Yeah, he's going to talk about finding the photonic circuits via maybe wait a little bit.
Okay. Is that coming through okay? All right, cool.
So, yeah, our next speaker is Marcos Levis, and his topic is finding the photonic circuits via delta weakening SMT.
Hi. Yeah, so this is some work I've been doing with Benoit Varon, and the idea is that we've been looking at this problem that exists in quantum computing, and in particular with photonic devices. And we've been kind of looking at it and trying to see what we can do with SMT solvers in order to see if we can tackle the problem. In this talk, I'll introduce the problem that we're kind of looking at. I'll introduce delta weakening SMT solvers as well, for those that aren't familiar with them. I'll then talk about a search algorithm we produce in order to solve this problem that we're investigating, and then I'll show some results that we've got from this. Yeah, so to start off with, when I talk about photonic circuits, what are these? And this is one medium for which you can perform quantum computing on. And the idea is that essentially you have some emitters over here, and you have a several number of wires or modes that you can send photons down. And so from these emitters, you send out photons, you then send them through this circuit in the middle here, and then you have some detectors at the end, and this kind of acts as your measurement medium for those that are familiar with quantum computing. And so, yeah, what this essentially looks like from a very basic perspective is that you have photons and you have wires, and you can send photons down your wires, and then there are two operations that you can perform. The first operation is a phase shift, and this involves rotating the photon in some way as it goes through that. And the second one you can perform is a transmission. So here you have what would be like a mirror, and through that mirror you have two wires going in, and then for each of them there's some chance that either they get reflected back into their own wire that they were in, or they get transmitted across here. And these are the kind of, so yeah, this one just rotates a photon there, and this one gives you kind of the probabilities that you can transfer across, or you get reflected back into your own one. Yeah, and so essentially with these components, you can build a circuit out like this, for instance. But given these components, and we know how to write them down mathematically, actually like coming up with a photonic circuit, you can get some unitary matrix out of it, and this is what is referred to as the transfer matrix. But also it turns out that given your transfer matrix, you can generate a photonic circuit from that. So really the problem of finding a photonic circuit is the problem of finding a suitable transfer matrix. Right, and so the problem that we're wanting to investigate is this. So we have quantum computing, and we have gates that we want to perform on qubits. And this is like the medium that we kind of write out over there. And then on this other side, we have this platform that we want to do it on, which is these photonic circuits, which are constitute of these transfer matrices over here. And we've got this transfer matrix, and this can kind of act on this sort of state where you're sending only one photon down a single wire at a time. And so in order to, these are kind of like, you can see the mass behind these is quite a bit different. And the way that we kind of join them together is through this thing called the Fock basis. And so this is where you can send multiple photons down a single wire. And so what we can do is then we can encode certain Fock states for our quantum computational states over here. And then we can actually work out how this state evolves based on our transfer matrix. So this matrix up here is entirely defined by our transfer matrix up here. So yeah, and the main encoding that is used for doing this quantum computing on photonic devices is the dual rail encoding. So for those familiar with quantum computing, but even those who are not, you kind of encode this 0 bit or this 0 qubit. You assign 2 wires to a single qubit, and the 0, 1 is assigned to the top wire, and the one state is assigned to this bottom wire over here. So you can kind of, so if you detect something in the top, you know you're in the 0 state. If you detect something in the bottom, you know you're in the 1 state for that qubit. And so with that, you can then easily extend this, because then if you've got q qubits, then you just need 2 q wires, where for every 2, you can kind of see here we've got 0 state, 1, 0. Here we've got the 1 state, this is 0, 1. But then if we want to have a second qubit, we can assign the 0, 0 state to be this 1, 0, 1, 0 state. So that's sending 1 photon through the first wire and 1 photon through the third wire. And then similarly, if we want to do 0, 1, you send 1 photon through the first and then 1 photon through the fourth wire. And yeah, so this is the standard encoding, but you can see I've also adjoined this suffix thing as well. And that's because generally you want to have some ancillary wires in a photonic setup. And so you can assign this to be some values here. So for instance, you may wish to have no working ancillary wires. You may wish to have one where you have no photons going down, like 2 wires, for instance. You can have one where you just have a single wire, but you're sending 3 photons down it. Or you could have one, for example, where you've got 2 wires and you're sending a photon down each. And you assign, whether you set your suffix to, that's what you assign your computational basis states to. And so for implementing these quantum computing gates, the idea is that you have this, you have your FOC basis operator over here. And the idea is that you want to make sure that your quantum computation operation is happening within those states that I showed in the previous slide. So it's only happening on those ones. And you don't really care what happens everywhere else. You just want your unitary one to happen in your quantum computing subspace up here. And the thing with this photonics thing, though, is that there's only a chance of this working, and that's what this alpha is. So this alpha acts as an amplitude on the operator, and your success probability is based on taking the modulus squared of it. And so one more thing I'll talk about, and I'll show 2 examples, is there are different methods that you can choose to measure your qubits as well, or your photonic devices. So the first one is this post-selection, where you're measuring everything. And then the second one is heralded, where you're only measuring your working wires down at the bottom here. And so these kind of give different, these change what sort of states you read out, essentially, and can affect what you, can affect the setup of the circuit. So to give a very basic example, so this is quite a common gate. This is called the CZ gate. And all it does is it applies -1 onto this last quantum state in the bottom right here, and then it just does nothing to everything else. But for the post-select scheme, this is the photonics setup for it. And so you've got 3 mirrors that combine with different wires, and you can see that the assigned matrix for it is quite a bit complicated. So this isn't like a trivial thing to do. And additionally, the success probability here is only 1/9. So it's not amazing, but that's actually the best that you can achieve. That's optimal. And then in the heralded case, where you're only measuring your your ancillary qubits, so in this setup here, these bottom 2 down here are your ancillary wires here. You're sending down 1 photon down each of them, and then this is the circuit for it here. And as you can see, like, this is you can see by the theta values in here, these are not common values, and so it's a bit tricky working out what these are. And so we want to see if we can use SMT to do this. So the general problem is, given a quantum computing operation that acts on a certain number of qubits, find a photonic circuit that implements that. That's the general problem. The problem that we're interested in is trying to find one that is also optimal. So finding one that acts on a dual rail system, you also have a number of ancillary wires you want, and the measurement mode as well. And then you want to find a linear optics operation that maximizes the probability of your quantum computing operation occurring. Okay, and so this is the setup, and so now I'm going to go into a bit more SMT stuff. This is probably about most of the quantum stuff you'll see in the talk. Yeah, so SMT solvers and T-real. Most people here are probably vaguely aware of SMT solvers, but I'll just give a quick introduction. The idea is that essentially you have arithmetic formula or formulas for various theories, such as strings, and you can join them together using logical operations. And the idea is that essentially you want to find values for your variables within your arithmetic expressions, and such that they satisfy your logical constraints as well. And so you have a dedicated theory solver that finds values for your variables, and this is combined with a SAT solver to make sure that it satisfies the logical constraints as well. And then you have different theory solvers depending on which domain you're working in, so reals, integers, strings, all this sort of thing. And so there are many software tools that are available out there, so Z3, YC, CVC5. When me and Benoit first started this project, we didn't really, even with simple examples, we didn't have much luck using these base solvers. So then we decided to try out what we could do with delta weakening SMT. And for those of you probably not very well aware of this, but I'll give some explanation. So generally, SMT has a tough time working out nonlinear expressions, which there are quite a lot of in our problem domain that we're looking at. And so these are terms that are like AB, A squared, A cubed, B squared, but also can include things like trigonometric and exponential functions as well. But we're just concerned with polynomial-like expressions. And so you might have something that looks like this, some sort of polynomial of your variables that equals 0. And so what delta weakening does is this introduces some perturbation into the formula. And so you want to instead make sure that your function, the modulus of this, is less than this perturbation delta here. And so if you apply this for all your functions or all your terms in your SMT file or the problem that you wish to solve, then it goes from an undecidable theory to a decidable one. And so there's some other constraints to this, though, in that you don't get sat out exactly. You get out delta sat instead, so your terms are now delta satisfiable, so they satisfy the expressions up to this term delta, but you still get unsat out, which is quite handy. And so D-real is a delta weakening SMT solver, and so it implements this technique, and so we can use this to investigate our problem. So now I'm going to talk about the search algorithm that we come up with for kind of generating these photonic circuits. And so firstly, I'll go through the encoding of the problem because this is probably a bit more interesting for some people. So firstly, we have introduced bounds on our transfer matrix and our success probability. This is just that the values are between -1 and 1. We then require that our transfer matrix be unitary, and so this is what this constraint introduces. So this is that the unitary and its conjugate transpose is 1 on the diagonal and 0 elsewhere, so just equal to the identity. And then the final thing that we need is we need our constraint that we want the Fock space to act like the quantum computational one. And so this is what this expression here introduces. And so this forms the core of our SMT encoding, that we have bounds on all our transfer matrix and our success probability. We have our transfer matrix being unitary, and our transfer matrix, when acting through the Fock basis, acts like our quantum computing operation that we want to implement on it, up to our value, our alpha here. And so this is an example of what the file looks like. And you can see up here, we've got our bound terms. Here we have our unitary terms. And then down here, we have some of the terms that relate to the Fock basis being equivalent to the quantum computing operation here. And then at the bottom, we have this extra term that we use for our search algorithm here. But I'll just comment on the encoding quickly. So core consists of mainly polynomials of degree 2 and the number of photons that are in your photonic circuit. The higher degree polynomials are based on the number of qubits and number of photons for the auxiliary. So generally, it'll be 2 times, no, not 2 times. It'll be your number of qubits plus however many you feed into your ancillary wires. And finally, that because we know that they're based on quantum computing gates, we can speed up the computation by adding or removing constraints, because we may have some information. Like for instance, if we know that the zero state, nothing happens to it, then we can add extra constraints that say that nothing needs to happen on the photonic device with that state there. Right, so we have our encoding now, and what we do is we then can submit that into DReal, and DReal will tell us either one of 2 things. It either times out and returns unknown, or it returns unsat, in which case the encoding is not satisfiable, i.e. we cannot find a photonic circuit that satisfies our encoding. However, the alternative is that DReal actually returns us some delta unitary matrices. And what this consists of is it consists of 2 matrices, one matrix that acts as a lower bound on every single matrix element, and then one that acts like an upper bound on every matrix element. So we kind of get this hypercube of matrices that are all delta satisfiable. The problem is that these matrices are not unitary matrices. And so the question is, how do we actually get a unitary matrix out from these 2 bounds that we have in order to get a valid optical circuit? And so the way that we do this is that we do this neat little trick where what we can do is we have our lower bound and our upper bound. And what we can do is we can take the singular value decomposition. Because the diagonal matrix, it acts very close to the identity. So what we can do is we can remove that, and then we just have 2 unitary matrices. And then that just gives us a new unitary matrix that kind of acts close. And so that's what this operation over here is doing. After that, what we do is then we can calculate the success probability of this matrix, and we can kind of like get out the quantum computing operation that simulates, and we can see how close it acts to you, and then we can use that instead. So yeah, and this is a really kind of neat unitary extraction technique to get from something approximate to something that you can actually implement. So yeah, and now for the search algorithm, so yeah, we take our encoding, run it on DReal. If it fails, then we either don't know if there was one that exists because it times out, or we know that our encoding or the setup that we've given it is infeasible. It's not possible to implement the gate that we want to on that device. However, if we get delta sats, then we call DReal again, and we see if we can find a better matrix. So we update, we add a constraint that lower bounds the success probability, and then we run dreal again and see if it can find something better. And then it doesn't really, and then either it will eventually time out or return unsat. If it times out, then we've still got a valid operation that we can implement. We just don't know if it's optimal. Alternatively, if we get unsat out, then that means that we know we're optimal up to our value of delta that we've implemented. And so we've come up with an artifact for this that's implemented on Python. Just another thing as well, we can also take our matrices and we can feed them into this tool called Percival, which is used by the photonics crowd. And that essentially allows us to get out diagrams of our circuits there. So I'm just going to highlight some experiments first. So firstly, I'm going to be mainly looking at post-select. So in the post-select scheme, we know that with a controlled Z gate, which is the one I introduced earlier, this, with no auxiliary wires, we know that this is infeasible to do based on our search, and these are very quick results that we can find. CZ with one vacuum wire, so that's having an extra ancillary wire with no photons sent down it. We also know that's infeasible. A CZ with two vacuum wires, we are able to replicate the known result, or the known result up to some constant, some change in phase, basically, that does nothing. But we can replicate that. And then we can also do similar results for the C0, which is a similar gate for that. And so these are the core results that we have for post-select, so that's what we start off with. Next one, we wanted to see what happens where if we have a single auxiliary wire, but we just send a whole bunch of photons down it, and what happens if we change that amount. So we have the same setup as we had before of the dual rail encoding, but now we include a wire that we just spam photons down. And with this, our tool is able to actually find values for quite actually a high number of photon counts as well. Keep in mind that when you get up to 30, like these values, 13 or 14, you're talking about 13 or 14 degree polynomials as well. So it's quite interesting that we're still able to find value within a few minutes that we're able to find this. And as far as where these seem to be the close to optimal values, and these kind of match results from this is from like a physics paper here. This matches results that they're able to get as well for doing a similar experiment. So this is quite nice that we're matching what's going on in the physics as well. We then also wanted to try what happens if we try a new gate. So we decided to look at this Givens rotation gate, which has applications in quantum chemistry. And so our setup was that we had our dual rail encoding as before, and then we have two auxiliary wires with no photons that we're sending down them. And the result is that as we change our angle in our rotation gate over here, we can see that we're able to, within a few minutes, get reasonable success probability out. And it's quite interesting that these are the we see there's sort of a pattern going on here. We're not quite sure exactly what this is. There's probably some theoretical reasoning behind why the optimal circuit is close to this, but we don't know that exactly. So these results have mainly been for post-select, where you're measuring everything. But for physicists, the ideal is to be able to only measure your ancillary wires and keep your working qubit section of your optical circuit. So we had a look at that. With this, we haven't got as great results. So firstly, the CZ with no or one vacuum wire, we can show that's infeasible, but that's very easy. The CZ with two vacuum wires, we're able to show it's infeasible with a quite low probability, but we still had a tricky time getting that. Once we start sending down photons, though, it starts becoming tricky. The CZ with one photon down it, we're able to show that's infeasible to implement with a heralded scheme. But then the result that was right at the start, the circuit that was right at the start, we're unable to get that out. So unless we run it for a long time or find some other way of getting around it, this is unknown, but it's known in the physics literature. So yeah. So just to bring some conclusions here, we've developed a general method for finding photonic circuit using delta weakening SMT solvers. We've come up with encoding and implemented into SMT lib, so we have generation, and then we can do our experiment execution within Python. We've shown that we can replicate known results and generate new results for post-selection at the very least. And so there are various improvements that can go on here. One thing that would be nice, this is more for just generally like SMT solving, having some sort of theory for complex numbers would be nice. We know that we can do it, we can get ours working for single qubit operations, but not higher. Another good target would be 3 qubit gates. We've been trying to look at that a little bit, but that blows up the too many formula and too high polynomials as well. We want to be able to try and replicate known results for heralded, but that's also, again, proving tricky. Finally, it would be good to find bounds for optimal results as well. And so what I mean by that is that given our delta satisfiable instance that we get out from D-real, it would be nice to show that the unitary matrix that we extract from that is bounded. The success probability doesn't change too much based on our value of delta. So yeah, and other things that we've been trying out recently, or things that we're kind of looking at a little bit, is investigating what happens if we have more complex ancillaries. So ones that are entangled here, if you might have seen this, this is what's referred to as this is kind of like a Bell state over here, but this is for photons instead, so it's referred to as a noon state. Here another thing that we're looking at is investigating single state generation. So rather than try and emulate an entire quantum gate, we're just trying to generate one state from it. So that generates fewer constraints, but that's still proving a bit tricky. Another thing that we're thinking about as well is submitting some of these benchmarks that we've got, because it's an interesting family of problems to SMT Comp, to have the SMT community kind of look at it more generally, because while this is nice that it works on this D-real, it would be cool if it could work on something like Z3 or YCs or CVC5. So yeah, that's my talk, and thanks for listening.
So we are almost done. So quick questions. Yes.
So this may be more like a comment. So you were complaining about this, the encoding of complex numbers, that the SMT solvers don't work well with them, and we have a good experience with using some algebraic encoding of the complex numbers so that the solvers can scale much higher. So I don't know whether it would be applicable also in your case.
As far as I'm aware, I know Z3, for instance, they have some algebraic encoding for the reals, but I mean,
there is an encoding where you can express the interesting complex numbers for quantums as some kind of a 4-tuple of integers with some scaling factor, and that's used, for example, in simulation.
Oh,
there's like
yes,
precise
yes,
simulation of quantum circuits.
Yes, are you talking about like the one where you have like essentially
you're like four.
Yeah,
like
you have four
vectors
different angles.
So we have experience like in synthesis. Then this is scaling much better than if you work with like pairs of reals or something like that.
Okay, yeah, that's another thing that we could potentially look at. That would be interesting to see if it could match up with this. So yeah.
More questions?
You say you are using D-real, but the DRAM has only real number. When you encode the unitary, you need complex numbers. So how you handle this?
So generally the problems that we've been looking at, we can restrict them for the real domain, but we can generate the complex variant of it, and that's just by having two numbers, one acting as the real part, one acting as the imaginary part, and then our generation is able to generate the complex version of a file if we want. A lot of what we've been doing is based on the real, just restricting it to the reals, and that works fine, but then the complex is kind of a bit trickier. So, yeah.
So let's thank Mark again.
We are receiving image on there. Can you?
Oh, it turned green.
Oh.
There we go. All right. We'll just do this, I guess. I don't know why it's not mirroring. But this should work fine.
So our last speakers of these sessions and also the VMCAI is Nick Vaduz. Yeah, he's going to talk about probabilistic verifications of modular net-on-chip systems.
All right. Well, thank you. Well, yeah, like I'm Nick, so I also know that I'm probably the last thing before some of you going home or going back to your hotel for the last time, so hopefully it'll be a good one. All right, so as a quick introduction for what we're going to cover today, I'll just briefly introduce the problem space. We'll talk about what on-chip networks are and our motivation for the probabilistic verification that we are doing. And then we'll move into talking about the modular network on chip model that we have developed. And we'll talk about our verification methodology, and then we'll wrap it up with some results, and should be done. So to get started, I want to talk about the need for on-chip networks, or network on chips, or sometimes we call them a NOC as well. So this graph here is just showing on the right side, this black line shows the increase in CPU processor speed. And I mean, this is for specific processors, but generally speaking, from about the 70s up to the early 2000s, you were seeing this really rapid growth in your processor. So what that meant was that every year, if you were Intel, you could just ship a processor that was twice as fast, and it still only had one core. In about 2002, we hit limits on that. And due to silicon, you can't really scale the clock speeds anymore. And so then we started adding more cores to our CPUs. So this presented a problem because all of your cores on a CPU need to communicate. They might be sharing memory, they might be sharing other resources as well. And the traditional communication architecture is a shared bus. So on this bus, you have all these PEs. These are processing elements. So these are your CPU cores, might be a shared memory cache, or today might be an AI accelerator. and then each of them have an interface to the bus. And if processing element 0, for example, wants to communicate with processing element 3, it's going to request exclusive access to the bus and then send information to it. And as we can see, as the number of cores grows, this shared bus really starts to slow down your chip. So instead, researchers developed these on-chip networks, which are a highly parallel method for communicating on multi-core systems. So in our example here, we have a 4-node system, and each node is a router, and each node has a processing element as well. And now we can have this more parallelized and sometimes asynchronous communication between each of our nodes. So specifically for our work, we look at a specific network topology, which is a 2x2 square mesh, or sorry, not 2x2, an n-by-n square mesh. This would be a 2x2. And in that mesh, we have these routers, and the routers are just in charge of routing packets through the network and determining where they go. We have the processing elements, which, as mentioned, they introduce new packets into the network. And then in between routers, we have these links. And so each link is made up of a channel, which is this arrow here, and that represents a physical wire. And on a wire, we're saying that a packet is sent across it during one clock cycle. And packets are sent across wires into these input buffers. So each router has 5 input buffers. They're not all shown on this diagram, but they'll be shown later. But it has one in each of the cardinal directions, and then one for the processing element. But these buffers are first in, first out hardware queues, where a packet is pushed into the back of the queue and then popped from the front to be used. And that's how packets are moved over those links. So the mechanism that a network on chip works is through packet switching. So processing elements generate new packets. They'll push them into the local queue of each router. And then the router will look at all the packets at the front of each of its queues. It will select one, pop it from the queue, send it across the channel towards its destination. So in our model, we use a specific methodology called XY routing. So this is super simple. First, packets travel horizontally across the network, and then they'll travel vertically. So for example, if processing element 0 wanted to generate a new packet, if it wanted to communicate with processing element 3, it would generate a new packet. The packet would be sent horizontally to router 1, and then vertically to router 3. And this is really simple. There are a lot more complex routing algorithms available that do dynamic routing or fault detection. However, those are a lot harder to implement on actual hardware. And so in a survey of real-world network on chips from the past couple years, about 40% of them used a variant of XY routing because it is sufficiently simple to implement on a network on chip. Additionally, it's known to be deadlock-free, and it's also deterministic, which are all great things for easing verification and hardware design. So the last thing that the routers do is they have to arbitrate between different packets. So if you have several packets that need to use the same channel, the router chooses which packet to send first. And again, we just use a relatively simple round-robin arbitration, which is kind of a priority queue based, just to ensure fairness among all the packets. Again, there are more complex implementations that you can do, but because we're implementing this network on hardware, oftentimes a simpler implementation is used to be able to describe the circuit that does that. So we'll talk about what we're going to verify with our network on chip model. So we're looking at power supply noise. So this is voltage drops and spikes in the network. And this noise is caused by traffic in the network, so either high traffic or high changes in traffic. And these spikes and drops can lead to erroneously flipped bits in the network, which can lead to dropped packets, corrupted data, or just in general, an increased latency. So this is a diagram from one of our collaborators, and it just shows that as the process node or transistor size shrinks, the overall peak power supply noise voltage goes from about 40% in this on a 32 nanometer node to about 14 or 80% on a 14 nanometer node. So if you're seeing these spikes that are about 80% of your average expected power, you're going to have this corrupted data. And we want to be able to provide upper bounds to this. So our contribution for today is we provide a modular network on chip model. That model is the NOC I previously described. It's written in the modest language, which I'll cover more in a second. We talk about CTL model checking for the correctness of the model. We talk about the replication of results from previous models. And finally, we'll look at power supply noise characterization for network on chips up to an 8x8 mesh. So we'll start with our modeling approach. So power supply noise is highly dependent on both the network on chip implementation as well as the traffic patterns that you see in the network. So network on chips are tightly coupled networks. So the behavior of a node in the network is highly dependent on the behavior of its neighbors. And it's really hard to separate out a node from its neighbors and analyze it by itself because of that really tight dependency. So modeling power supply noise requires the right level of abstraction when looking at a network. So we think that the correct level of abstraction is to include all the routers so that we can model the tight coupling across the network, but not to include all the circuit details. And given that, there's three kind of general approaches to modeling power supply noise. So there are semi-formal approaches that use a combination of simulation and based typically on the behavioral model of the circuit that is then synthesized into a power level model. And these can provide maybe interesting results and potentially some bounds on the power. However, the simulation often cannot provide any kind of statistical bound because you just can't do enough runs with the simulations. So some previous formal approaches were a monolithic style 2x2 mesh network on chip written in the modest language. So this was the inspiration for our work. This network on chip kind of showed a potential power supply noise characterization method, and it also showed that generally this abstraction seems to be feasible in modest. However, it wasn't scalable, and a 2x2 network is really small. Typically, you're going to see networks that are at least bigger than 6x6 to accommodate all the cores and caches and stuff on a chip. So our approach is a modular network on chip, again, using modest. So a quick aside about modest. So modest is a probabilistic modeling language, and it is a high-level language in the sense that it provides to you high-level constructs such as parameterized processes and functions and high-level data types. And then it takes your high-level data types and processes, and it can convert them into an underlying representation. So for our case, we use a DTMC, or a discrete time Markov chain, as our underlying representation. But modest can do other things such as MDPs or CTMCs, but we don't need to use those. Oh, and the reason that we chose to use modest as opposed to a tool like Prism, which is another probabilistic modeling language, is that modest has really rich support for data types, as we'll see in a little bit. Okay, so let's look at how we characterize power supply noise. So this will introduce the properties that we use to characterize power supply noise, and then we'll show how that applies to our model. So there are two main components of power supply noise. So there's resistive noise. So this is relative to the inherent resistance of any circuit. All circuits have some level of resistance, even just wires do. And additionally, it's relative to the current at any time in the circuit. So inductive noise, on the other hand, is relative to a change in current over time and the inherent inductance of the circuit. So based on some previous work by our colleague, we can abstract resistive noise in our model to be relative to the current cycle activity, where the activity is defined as the number of packets sent or received during a clock cycle. And additionally, we abstract inductive noise to be the change in packets over 2 clock cycles. So if you send 5 packets on clock cycle 1, that would be your resistive noise for clock cycle 1. And if on clock cycle 2 you send 2 packets, that change would be an activity level of 3. So then with those activity levels, we'll use probabilistic computational tree logic on our DTMCs with bounded reward properties to measure the power supply noise over a set of clock cycles. And so the first thing we do is we aggregate the noise, which is router specific. We aggregate it all into a global count. We have two counters, inductive and resistive. And so every time any router exceeds an activity threshold, we increment one of those counters for the noise. So then once we have those global counters, then we calculate our properties of this form, which is stating that we're looking at the probability that within m clock cycles, the noise, or the count of noise events, is greater than or equal to k. And so here on the left, what we're looking, or on the right, what we're looking at is an example of k is 1, 5, or 10. This is on a 2x2 network on chip, and this is the inductive noise. And so we can just see these sweeps. Oh, and this is a CDF, I guess. As we sweep over the number of clock cycles, we can see the probability of exceeding this number of noise events just increases over time until eventually we'll reach 1. Okay, so now that we kind of know about power supply noise, we can talk about how the network on chip is modeled in the Modest language. So we define a n-by-n network on chip as the parallel composition of n-squared router processes, the Modest language. So for a 2x2 network on chip, it would just look like this, where we're taking 4 routers, and we compose them in parallel along with a clock process, which is what we use to track the elapsed time. And this is kind of our first look at the Modest language. So here we're declaring a parameterized router process. It's parameterized by an identifier. And then here in a parallel block, we're composing 4 of them together. So just as a quick review, the components that we see in a router, where we have the 5, or we have each router has a processing element. And then we also have our 5 buffers in the cardinal directions and the local buffer, along with our 5 channels. And those make up the links between both the processing element as well as the neighboring routers. And then additionally, we have internal logic for routing and arbitration. And so the execution of a router in Modest is modeled by the serial composition of several processes that define that routing and arbitration behavior. So what that looks like is like this, where we just have the semicolon is the serial composition operator in Modest. So we just compose in serial all these sub-process calls. They're all parameterized by the identifier. And then this last recursive call to router is how we simulate infinite execution in the model. Or I guess how we model infinite execution. So briefly, we'll touch on why we use these router identifiers. So these router identifiers, because we have this fixed regular mesh, we can go from an identifier into coordinates, and then we can go from coordinates back to an identifier. And so this provides us a great way to modularly define both the traffic patterns that we want to measure, as well as if you want to define like router-specific routing algorithms, you could use this as well. And then additionally, the network on chip state is just stored as a global array, where each router is just an element in that array, and we can index it into it by the identifier. So let's talk about we'll look at one of the sub-process calls. So look at generating packets. So the generate packets process models a processing element connected to a router. And so it injects new packets into the network. And it's a primary source of probabilistic behavior for the model. Actually, it's the only source of probabilistic behavior for the model, because you determine probabilistically both whether or not you will inject a new packet, and additionally, you have to determine where that packet is going to be sent to in the network. So this is kind of a quick sketch of what the process looks like. If the local buffer is full, we're going to do nothing. Otherwise, based on some probabilistic condition, we will send or we'll add a new packet to the router with a probabilistic destination X. And in our work, we just use a uniform destination because there's not a lot of work on what real-world packet distribution looks like in network on chips. We won't cover the rest of these sub-process calls, but you're welcome to look at our paper for in-depth look at them. But as a quick basics, we have this prep router sub-process. This sets some state flags so that we can maintain a synchronous update. Advanced router actually sends the packets. Update priority is how we handle arbitration and fairness. And then update global noise tracking is how we measure power supply noise. Then the last thing that we haven't talked about is this next clock cycle. And this is a synchronizing action that we'll cover more in a second. So the clock process just looks simply like this. And the clock process is in charge of controlling the stepping of time, or clock cycles, in the model. And so how we do this is through a reward, transition reward in the underlying DTMC. So a transition reward works on a specific transition, in this case, the next clock cycle transition. We just set this reward to be equal to 1. And then what we can do is we can just take a summation of that reward over the execution of a path. So in this path, for example, we have 2 next clock cycle transitions. So on those transitions, the sum of the reward will increment by 1, and we'll move through there. So then if we use this bounded eventually with the sum of the reward here, we can correctly calculate our bounded properties. Okay, so then the next thing we'll look at is some of the CTL properties that we verified. So some of the basic properties is we looked at verifying that there's no buffer overflow. We're modeling hardware buffers. And so while in the model, the modest language supports arbitrary length arrays, we don't want to exceed a maximum size that we've specified. We also want to ensure that each channel is only used once during a clock cycle. As for digital circuits, each wire can only be driven once during a clock cycle. We want to ensure that all the packets that are generated are correct. And we also want to ensure that our priority list is valid. So when we first went to implement these CTL properties, we ran into issues with the modular model seeing a much greater state space than the original monolithic model, or the old concrete model, for a 2x2 network on chip. And this was concerning because we really wanted this to be a scalable model. So the reason that we were seeing this expanded state space is between semantic differences between our network on chip model and the modest language. So modest is based on an asynchronous process algebra, whereas NOC, or network on chips, are modeling a synchronous digital hardware. And so as kind of a quick demonstration, this on the right is just showing the digital hardware, where we have all of the updates happening synchronously on the rising edge of the clock. Whereas here, we have the modest execution model, where you have to explore each update independently because it explores all those interleavings. So our end goal is to actually eliminate these interleavings, because for a digital network on chip model, they're not really interesting for us. And additionally, another issue that we saw before we fixed this synchronization issue is that if we look at the previous work of the monolithic 2x2 model, our modular model, when instantiated with a 2x2 network on chip, produced really incorrect power supply noise results. And so we wanted to fix those. So the way to fix that is that we introduce synchronizing actions, which are available in both the modest and Prism languages, and they kind of act like an action in a label transition system. And we introduce these actions into all state updates, so that all the state updates that we care about happen synchronously across every instantiated router in the network. And doing so, this just really reduces the state space that we're looking at. So we'll skip that example for now. But this is a quick look at for CTL model checking our 2x2 network on chip. So the asynchronous original version that we implemented without any synchronizing actions, we ran out of memory at about 126 gigabytes after a little bit more of a day of model checking. And composed to our synchronized model, we were able to do the model checking in about 10 minutes and use about 10 times less memory. And additionally, implementing these synchronization actions resolved our expected power supply noise with the modular model when instantiated for a 2x2 network on chip now matches the behavior of the monolithic model. So if we want to look at some of our results, we were able to instantiate 3x3, 4x4, and 8x8 network on chips. And while on their own, these results aren't particularly interesting, we can see the expected use case here, where as we get into larger network on chips, the power supply noise, the rate of change of the noise is much greater. for larger network on chips, and this just occurs because in this global measure, we see more packets overall in a larger network. And so additionally, we have another measurement strategy where we're looking at individual routers in a network. So in a 3x3 network, we have 3 types of routers. We have corner routers, edge routers, and a central router. And in this case, we've been able to generate these power supply noise CDFs for each type of router in the network individually. And because we have a little bit of time, we'll look at, I wasn't sure if we'd get here, so look at some future work that we're looking at doing. So we want to characterize power supply noise for different traffic patterns. There's some recent work late last year in a survey of traffic patterns in network on chip. A survey like this hasn't really been done before because networks on chips they are so different across the industry in terms of their use cases. But since they've been around for a long time now, they have enough information to do this survey. So we'd like to implement some of those findings in our model. We'd also like to use simulation level results to relate our abstract model back to a more concrete measure of current and voltage. So previous work had showed that the power supply noise can be abstracted down to just the activity level of each router, and we want to be able to go in the reverse and potentially provide a real current value of upper bound. And then the last thing that we'd like to do is develop potentially an abstract router for verifying larger networks with CTL model checking. And that's all. Thank you.
So, any questions? No, last chance in VMCAI. Okay, good.
Thank you. Now, how do you think how hard would it be to use this for different types of NOCs, for example, octagon and so on, the different layouts?
Yeah, so we have considered some. We actually because originally we restricted it to a square mesh style network on chip, but it works for rectangular ones. To transition to different ones like an octagon or rings or anything like that, it would require some model changes in terms of the data structures used, because our data structures are based on having 5 buffers and 5 channels. But I think it should be relatively possible in the modest language.
Okay, thank you.
Mm-hmm.
More questions? Okay, so let's thank Nick again. Yeah, let me also thank the organizers, the Thomas, and Yifang and Ondras.
Yes, and I'll just also say thank you to all the speakers. I think and also for all the participants. I think we've had an excellent VMCAI. I think the conference is doing very well. At least that's what I suggest that we report back to the steering committee, so that we are sure that there'll be a VMCAI next year as well. But until then safe travel back if you leave now, and perhaps for the other ones, see you tomorrow.